Okay, so I believe we can start going through now. Damani?
Mr. Ka or Da?
Mattis.
Oh,
Yes, sir.
Yes, all the questions going. Finish everything?
Yes, sir.
For question one?
No, not for question.
For question one, okay. So
Sir, I was having trouble on
repeat?
so I was having trouble on the same thing again.
Okay. So that's why we're doing these questions, to get ourselves, enough practice. Janelle?
It's question 4.
Question four? So you've answered up to question four?
Yes, sir. Except for the for the circuit diagram.
Oh, okay, cool. All right, so we're gonna start going through right now. Did anyone in particular have any difficulty and was probably unable to answer any question at all? Yes, go ahead. Oh, yes, I see you raising an Brookie. What sort of difficulties you had? Okay. Were you able to do the graph question? Okay, all right. So let's start going through. So was anyone able to complete all the questions?
Sir, for this, for number one.
Repeat.
For number one.
Well, everything in general, the entire questions.
No, sir.
Okay. But how were you able to work the questions, Kara? You had completed question one?
Yes, sir. Completed question one. I started question two.
Okay. All right. So, if you went through the paper, you will see that there are more than 6 questions, right? And I deliberately did it like that, so we have questions that covers as broadly as possible in terms of the topics that were posted, right? To give everybody a chance to get exposed to different areas. So what I'm going to do, in terms of the graph, we're going to discuss the graph now. So what I'm going to do, I'm going to switch my screen and we'll discuss the graph. So let's do that. All right, so my screen is up. Confirm for me.
Yes, sir.
Yes, sir.
So it says here that the activity of a radioactive sample was measured over a 24-day period, and the results were recorded in table 1. Let me bring this over a little bit. The results were, hold on. The results were recorded in table 1, as we see right here. Now, okay. So now, let's see what they say we need to do now. All right, so they say, so we have our table right here. So we have the time in days, we have the activity of the sample. What's the unit for the activity of the sample?
Seconds.
Seconds. All right, based on the table, what's the unit here?
Time. Days, sir.
No, time is the
Day.
time. No, hold on a second. Time, yes, the unit for time based on the table is days. For the activity,
Oh.
what's the unit?
Seconds.
Not seconds. Look in the table. Look at the heading of the table. Repeat.
Disintegrations per second.
Right, disintegrations per second. So we want to be mindful of those things, especially when we come on to plotting of the graphs, because we have to include our units number one, the quantity as well as the unit. So once you're given a table, you always want to pay attention to the quantity. In this case, it is time, and the unit for time is days. Similarly, we have the activity right here as the quantity, which is the activity of the sample, and the unit is disintegrations per second, right? So as I said, we want to be aware of these when we're plotting off the graphs, because we're going to be required to include these labelings in our graph to ensure that we can secure maximum marks. All right, so we have the time right here up to 24 days. We have the activity starting at 40 disintegrations per second down to 5 disintegrations per second. So this question deals with radioactivity, right? So we're required to plot a graph of radioactivity. All right, so it says we're to plot a graph on page 3 of activity versus time. Now, by now, we want to be aware that whenever we're given a question like this, a graph question, and we're told to plot something versus another thing, in this case, we're asked to plot activity.
Y-axis and
Repeat.
x-axis.
Repeat,
You have
please.
to look at the y-axis and you have to look at the x-axis.
Yes, we look at the y-axis and we look at the x-axis, but more importantly, we have to determine what quantity goes on the y-axis, what quantity goes on the x-axis, and we can determine that based on the statement that we're given. So based on the statement right here, how can we determine what goes on the y, what goes on the x?
Activity go on the y and time go on the x.
Right, and how do we determine that? How do we make that decision?
Because activity comes first, so that is y, and time second, so that is x.
Okay, so activity, so whatever comes first in the statement given will always be going on the y-axis. So activity in this case, we're going to place it on the y-axis and time on the x-axis. Is that clear to everyone?
Yes, sir.
Okay. Activity on the y, time on the x. So what to do next is we're going to start by drawing in our axes. I've already done that to minimize the time that we're going to have to spend on the graph. But you will draw in your axes, your horizontal x-axis, your vertical y-axis, right? And notice the first thing I do after labeling the axes x and y, I indicate the quantity. So we're going to have time in days and activity, right? So we're going to place the quantity just as we did for time, and we're going to also have to place the unit. What's the unit we said that is going to be for activity again?
Disintegration.
Disintegration per second.
Disintegrations per second, right? So we can write that as a symbol. We can write it as S to the -1, which would stand for disintegrations per second, or we could actually write out the entire unit. But as it is right here, this is fine. Disintegrations per second. Now, after we have done that, we need to select a suitable scale so we can plot the point. So let us say we start with the x-axis. So we have time going from 0 to 24. So we need to select a scale that once we plot from 0 to 24 on our x-axis, we're going to be able to cover at least 50% of the x-axis. The points will cover at least 50% of the x-axis. So what we can do is we can go down to our axis and we can say, okay, we can try possible different scale ratios. We can maybe say 1 centimeter to 1. So that simply means every 1 centimeter on the graph page, we're going to increment by 1. So we could try that and see what would happen, right? Because sometimes, choosing the scale might become a little bit challenging. So I'm sharing with you, ways you can use to actually determine your scale. So you can maybe say 1 centimeter to 1 day. So you will count up. So you would count up for 1 centimeter. For 1 centimeter block, you would count up, right? And you say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the maximum we can get up to is 18 using 1 centimeter to 1. So maybe that will not work. Okay?
So I use 2 cent. I use 1 centimeter to 2 units.
1 centimeter to 2. So right, so we could say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Right, because we need to go up to what, 24 days, correct?
Yes, sir, 24 days.
Right, so we could use 2 centimeters to 4. Now, personally, I like to use, 1 centimeter to 2, sorry. Personally, I like to use 2 centimeters, right? Because it just allows me to space up the points better. And and again, if I were to use 1 centimeter, it's going to be kind of jumbled up on this presentation right here. So I like to use 2 centimeters. So if we're using 1 to 2, that would also correspond to 2 to 4. Agree?
Yes, sir.
Right? So we could say 4, 8, 12, what's next? 16, 20, 24, 28, and 32. Right? And again, once we have indicated the scale, or once we have inputted the scale, we want to state the scale that we're using. So let me just use a different color for this. So we said this was what? 4, 8, 12, 16, 20.
Sure. 2 units equals to 4 centimeters.
Okay? So, well, the other way around. 2 centimeters equals 4 units. Now, in this case, what's our unit for the x-axis?
Days.
Huh?
Days.
This.
Days, right? So we say 2 centimeters is equal to 4 days, right? Similarly, for the y-axis, we can do the same thing. So we're going up to 40 disintegrations per second. So maybe we can try just say maybe 1 to 5. Let's see how that works. If we say 1 to 5, we're going to have 5, 10, 15, 20, 25, 30, 35, 40. Now, using this scale is going to cause the y-axis to be small. So we're not going to be able to use that scale. So what?
So I use 2 centimeters to 5 units.
4 the time.
Repeat?
I use 2 centimeters.
Wait, there are 2 persons speaking. 1 person.
I use 2 centimeters to 5 units.
2 centimeters to 5. So every 2 centimeters we increment by 5. So we could say for every 2 centimeters we would say 5, 10, 15, 20, 25, 30, 35, 40. Right? Which looks to be more than half of the graph page. So we can go ahead with that. Right? So we could say 5, 10, 15, 20, 25, 30, 35, 40, 45, and up to, well, not 150, 50, right? 50. Sorry, I keep on writing 150. 50. Right? So that's our axes, right? And also we need to indicate the scale here, so we don't want to forget that. So in this case, we're using 2 centimeters equal 5 disintegrations per second. So we could say 5 s to the minus 1, just like that, okay? Fair enough?
Yes, sir.
Right, then it's just a matter of plotting the points. So looking back at the table, we just plot accordingly. So the first point corresponds to when the time is 0 and activity is 40. So we just put that in quickly. So 0 on the x, 40 on the y, so that will correspond to this point here. So we just place an x. And remember, when plotting the points, the accepted symbols, or what are the accepted symbols for plotting of points? X or
A dot with a circle around it.
a dot with a circle around it. So let us say we use an x. So we're going to have x right here. Next one, time is 4. Disintegrations, or activity, sorry, is 29.5. So we can find 4 easily on the x-axis, but we need to find out 29.5. So now, that's usually where we have a little challenge in finding those in-between values, because we can find 4 easily on the x, so we know 4 is going to be right, and we're looking for 29.5. So what we can do is we can determine what's the value of our in-between values, right? What's the value of these small divisions going up? So to do that, we say, okay, what's the difference between our 2 intervals? So the difference between 0 and 5 obviously would be what?
5.
5. So now, to find out the value of each small increment between those 2 intervals, we divide by the number of increments. So in other words, we're going to count up our increments 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we divide here by 10. So we say 5 divided by 10 is 0.5. So therefore, each small increment is 0.5. So
And so for my x-axis, I say 5 into 10, 2 into 5 for the x.
2 into 5 for the x. All right, hold on a second. Hold that thought. Let's gonna come back to that in a minute. So we say 5 divided by 10, and we get that each small interval is 0.5. Everybody's clear with that? We're making sense so far?
Yes, sir.
All right? So that means that each small division is 0.5. So if we have 25 right here, we're gonna have 25.5, 26, 26.5, 27, 27.5, 28, 28.5, right? 29, and then 29.5. So therefore, this small division just before we reach 30 would be 29.5. And that should correspond to 4. So it's going to go like that. Cool?
Yes, sir.
Okay. Are we good so far?
Yes, sir.
All right. So let's go through the others quickly. Let's go through the others quickly. So we have 8 to 20. All right. So 8 is right here. 20 is here. So we go like that. Next one is 12 to 14. So 12 to 14. So this is 10, right? 10, we're going to have 10.5, 11, 11.5, 12, 12.5, 13, 13.5, 14. So we go right there. Next one is 16 to 10. So 16 to 10 is there. And then 20 to 6.5. So we have 20, this is 5, 5.5, 6, 6.5. So we'll go right there. And then last one now is 24 to 5. So 24 to 5 will just be right here. So now, once we have our points, right, notice our points are giving us, signs of that characteristic curve, which is what we expect for a graph of radioactivity, right? Yes?
Yes, sir.
So what we do now is with our pencil, and we're going to make a smooth freehand curve, right? Now, what you don't want to do is you don't want to try to connect all the points, because you're not going to get a very smooth line in connecting the points. What you want to do is to just look at the points and with your pencil, try to make your best freehand curve, right? Based on the trend of the point. So let us say let's say we can try to get that now. So we take our pencil, right? And advice, one second. Bit of advice, what we can do is we can start from the lowest and just smoothly go up, because at least, we can actually view the points as we're making the curve this way. So we've placed right here, place the pencil right here, and just watching the points, try to make a nice freehand curve. Because, if you try to go at it this way, your hand is going to actually block the points. So you have to be stopping and, trying to check to see, okay, where the points are. That's if you're right-handed. Because if you're left-handed, it probably would be easier for you to go at it this way. So, because I'm right-handed, I would start here and just following the points, right? And let me just try. And sometimes, you have to do this several times. So what you want to do is when you're making your curve, try to do it lightly. And then once you have said, okay, this looks like a nice curve, then you sort of brighten it a little bit. So let's go at it. So we go like this. All right, let's try again. So as I said, sometimes, it might take several tries to get, one that you'll feel is the smoothest looking curve. All right, my hand keep on shifting a bit. All right, so it's going to be a little bit challenging for me on this platform, because the thing is kind of keep on shifting. So let me try again. All right, let's try again. All right, like about that. All right, how does that look? How is that looking?
Sir, in this case, you wouldn't draw a line of best fit.
No, not a line of best fit. Again, because of how the points are, right? Because the points are giving you that characteristic curve, you will have to draw a curve, right? Because when you plot the points, you can basically observe and actually determine if it is that you're supposed to draw a straight line or a curve. You know, based on how the points are, we expect to draw a curve. So we just draw a smooth curve, right, through the points, right? Something like this, okay?
Yes, sir.
Okay? So now, once you have done that now, remember, we have to close off the graph with a what? What is it we need to close off the graph?
Sir,
With a
title.
title.
Title, right? So we're going to place our title, right? I'm going to place my title here. So we say graph showing right. In this case, we just place what's on the Y, which is the activity. Activity,
Against time.
right? Activity against INST time, right? So it's a graph showing activity against time. Just a simple title to tell the examiner, okay, what this graph is about. So it's a time, T-I-M-E, graph showing activity against time, right, like that, sorry. So graph of activity against time, right? Everybody was able to get their graph like this?
Yes, sir, but the only thing I centimeter.
Oh, right. So again, it all comes back to the table, right? So you always be able to find out the unit, right, from the table. So always check with your table once you're plotting your graphs for the units, because you don't want to slip up and lose any mark unnecessarily. All right. So this is our graph. Now let's all right. So let me do, I think, the screen, double screen, so I can go back and forth, or full screen, I should say. So I can go back and forth. So this is the question, or these are the questions, and the first, after we have plotted the graph, next thing they say we need to do is to use the graph to calculate the average half-life of the sample that is determined from the average of 2 or 3 values. So to do that, we're going to go back to the graph, right, and we're going to say, okay, since we want to find the half-life, right, the average half-life, we have to have an idea of exactly what is the half-life. So what's the half-life?
So you have to take the original length and divide it by 2.
All right, so again, hold on a second. Hold on a second. So what's the half-life first? Let's start there.
The half-life is the time taken for half its original sample to decay.
Okay, so the time taken for the activity or the mass of a radioactive substance. So the time taken for the activity or the mass of a radioactive sample to reduce to half of its initial or its previous value. All right, so in this case, they want us to find the average half-life, and we're going to do that by considering the at least 2 or 3 values for the half-life, and then we'll find the average. So now, what we do is we're going to say, okay, in this case, from our graph, we can see that the initial activity is 40 disintegrations per second. So our initial activity, right, initial activity is 40 disintegrations per second. So what we do is we're going to say, okay, what would be the activity after 1 half-life? What would be the activity after one half-life?
It,
Repeat?
it is.
All right. The question is, what's going to be the activity after 1 half-life?
Sir, 20.
20, right? Which is half of the initial value. So after 1 half-life, the activity is going to fall down to 20 disintegrations per second. So what we do is we're going to take our ruler right? And we're gonna line up from 20 disintegrations per second. Then we're gonna make a broken line straight across like that to touch our curve. Then once you do that, we go straight down to the x-axis to actually find the time, the corresponding time when the activity is 20. Okay? So now, once you do that now, we're going to say, okay, when the activity was 40 disintegrations per second, the time was 0. So we can say then now that our half-life t, let's say half-life t, so this is the first value for the half-life, is going to be equal to, so when the activity was 40, the time was 0. Then when the activity went down to 20, the time is 8 point, this is 8 point, let's see now, this would be 8 point what? That would be 8.1. Huh? Anyone know?
8.8.
8.8, right? Because using the same idea, we have 0 and 4 as our interval. So the difference of 0 and 4 is 4, and we say 4 divided by the number of divisions, so we're going to get 4 divided by 10, which is 0.4. So this will be 8, 8.4, 8.8. So t, first half-life is going to be 8.8 days minus the time when the activity was at 40, which is 0. So in this case, we get 8.8 minus 0, which works out to be 8.8 days. Right? Normally, we don't show the subtraction here because we know it's going to be 0, but for the sake of explaining clearly and fully what's going on, we did the subtraction there. Anybody have any question on what we have done so far?
So I get a different value. I get when it was 6.8 for the first half-life.
Okay, no problem. And that is why the examiner said, you know, we're going to do an average, because based on how you draw your curve might determine the value that you obtain for your half-life. So again, it's the principle that we want to master and appreciate, not so much the precise answer or the exact answer. All right? Are we cool?
Yes, sir.
Right? So now we can find a second value now using the same concept. So we can say, okay, the activity is now at 20. After another half-life, it's going to be,
Sir.
yeah. You said repeat?
10.
10.
10, right? So same thing. So we'll go down to 10
Sir.
quickly. Yes, Kavon?
So you can go over how you got the 0, please.
Okay, yes, I'm going to go over it once more. Hold on a second. Let me just put this in. All right, so we do the same thing. Go across. And then we go straight down.
So we just divide by 2 each
Yes,
time.
yes. So you could start with initial activity and divide by 2 to get a half, because after each half-life, the activity, or it could be the mass, it always reduces by a half, right? So what we're saying now, Kevin, back to your question, what we're saying now is that, all right, what we have to do is to find the half-life, we have to subtract the time, right? Between when the activity in this case was at some value, right? And the activity when and the time when the activity is half of that value. So in this case now, we considered that initially the activity was at 40. After one half-life, it drops down to 20. Now the time when it was at 20 is 8.8. And the time when it was at 40, which would be the initial time, is 0. So we subtract 0 from 8.8 because we're going to subtract the final time, which is 8.8 right here, or the time when the activity would have dropped to half of the previous value, in this case 8.8, from the initial time, right? When the activity was, in this case, 40 disintegrations per second. Clear?
Yes, sir.
Right? So now we might be able to see it better here. So in this case now we're going to say, okay, the activity, or sorry, when activity is 10, the time here is 16.4. So we can say 16.4 days, and we're going to subtract that from the time when the activity was 20. Okay?
Yes, sir.
So we always subtract the previous time from the current time. So this now was 8.8, so we say 8.8, and this now would be what? Like 8.4? So,
Yes, sir.
or is it less than that? Is it 8.8? No, you're going to be like 7.6, right? Or something. Is that so? Check it for me.
Yes, sir.
7.6?
8.4, sir.
7.4?
Sir, 7.6.
Okay. All right. 7.6 days. All right. So now we can do a third one if we choose to, right? But let's just say we go with these two. So what we will do now is find the average. So we can say now that the average. So we can just say the average half.
Add them and divide by the total.
Right. So the average half-life then now will simply be equal. So we add these together. So we have 8.8 plus 7.6 divided by 2. And this works out to be what?
8.2.
8.2 days. Right? So my average value for the half-life was 8.2. What were you guys getting for this one?
Sir, I got 8.
8, okay. Anybody else?
Sir, I also got 8.
Also got 8, okay. So we see, we're centering around, a common value, around 8. So that's good. All right. So let's go back here. So let me just switch the screen. Window here. All right. So let's continue. All right. So we did that a while ago, and we got the average value to be 8. Now,
So I get 8.2.
that's fine. That's fine. All right. That's fine. All right. So let's continue. Let's continue. Let's continue. All right. So.
Sir, can you do the values in 3 half-lives? Because
Yes,
I
it
did
could be
manage
3.
to
You could do 3 because I said average of 2 or 3. So you could do a third one and then find the average. How many did you do?
I did 3 of them, sir.
3? Okay, and what was the average value?
I got 8.
Yeah, man, perfect. 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 All right. So now, all right, we had one more question. It said use the graph to determine the activity of the sample after 25 days. So I have to go back to the screen, to the graph, sorry. Thought we were done with this. All right, so let's say after 25 days, right? Okay? Yes?
Yes, sir.
So since I said we're to
Yes,
use the graph, now what we have to do now, based on this graph, what we might have to do is to sort of extend this curve a little bit, maybe like that, right? And then determine the activity after 25 days. So this is 24 days right here. So we're going to have 24.4, 24.8, 25.2. So 25 days is going to be somewhere in the middle here.
So,
Yes?
yes, sir. I get 3.6 seconds.
Okay, that's good. That's good. So we take our ruler, right, and we extrapolate. So we go to the graph, right, and then go straight across. And for this question, it's not so much the answer per se, it's just your ability to find the activity after a certain number of days by showing it on the graph. So in this case now, I would get about 5.5 days for mine. What were you guys getting for this one?
5.
5, okay. Anybody got anything different?
I got 5.6 days.
Right, good. Right? So
I got
that's
5.
5, right. So that's good. That's good. So it's about 5 days. All right. So going back now. So it will be about 5 days. Now, we could also maybe calculate this, So let's say from the graph we got 5 days. We got 5 days from the graph. Now what I'm saying is that we could actually calculate this by appreciating what exactly is the half-life. So let us say, after 25 days, right? So based on our calculation, we got our half-life to be about 8 days. So the half-life was about 8 days. So now, if we say, all right, after each 8 days, the activity reduces by a half. So now we can say, all right, how many half-lives will be completed in 25 days? So we can just say, all right, 25 divided by 8, we're going to get roughly 3 point something, right?
Excuse me, sir.
Yes.
Sir, the question said we're supposed to determine the activity after the 25 days, sir. So are we supposed to use like the 25 days on the x-axis and in the y-axis?
Yes, that's what we're supposed to do. Right? I'm just showing you that, okay, we could also do a little calculation to, see what we would actually get by our estimate via calculation, because sometimes they might ask you to estimate the activity and you can use the graph or you can do a calculation. Okay? Yes?
Yes, sir.
Right? So what we're saying now is we want to know, okay, how many half-lives will be completed in 25 days. So we divide 25 by 8, we're going to get 3 point something, right? So roughly 3 half-lives, right? So now, if the sample was initially at 40, the first half-life is going to go down to 20. Yes? All right, is that a question?
Where are you using the 8 from?
Repeat.
Where are you using the 8? The 8.
8 represents
We divide 25 by
the 8 represents the half-life. Right? A half-life is 8 days. Right? And we're trying to see, okay, how many half-lives will be completed in 25 days. Cool? Cool, talk to me.
Oh, thank you.
Right? So now we're saying roughly 3 half-lives will be completed. So after the first half-life, it's going to go down to 20. After the second half-life, it goes down to 10. And then after the third half-life, now it's going to go down to half of 10, which is? Which is?
5.
5, right? So we see that, both values, correspond. And
Five, sir.
right? So we see, can I appreciate that? Yes, no?
Yes, sir.
So next one now says that we're to state 2 types of emissions. Question? All right, so we want to state 2 types of radioactive emissions. What can we?
Alpha decay and beta decay.
Right, so alpha decay. Or let's say, well, no. let's kind of be careful with this. It says types of emissions, right? So the types of emissions we have are the alpha particles, right? Beta particles,
And beta particles.
right? Or gamma rays or gamma waves, right? Beta particles.
X-rays too, sir?
No, those are not radioactive. Right? Alpha, beta, and gamma are the 3 types of radioactive emissions. Right? Now, if they ask about decay, now we could say alpha decay, beta decay, or gamma decay. Right? Cool?
Cool.
Right? So, which type of radioactive emission is most dangerous to human tissue?
Yeah, for particle.
Repeat?
Yeah, for particle.
Sir, gamma?
Beta decay, sir. Beta particles.
Okay, all right. So let's justify why we say that. So why we say beta?
Because beta, they are hazardous when they inhale and swallow.
Okay, but it asks
Because beta particles can travel through few meters.
Beta.
So alpha particles would have high ionizing content.
Okay. All right. So we have some arguments in terms of the alpha and beta. But let's just kind of look at each in detail. So let's say we start with alpha. So we know that alpha particles are highly ionizing, right? They are very ionizing. So that simply means as soon as they come in contact with atoms, they quickly strip away electrons from them, making them or turning them into ions. So they're very ionizing, right? Because remember, an alpha particle is what? What's an alpha particle?
Sir, helium.
Right, an helium nucleus. So that simply means that it lost two electrons. So it's like we have an helium atom that has the last two electrons, so it wants to quickly get those back. So it's going to quickly ionize atoms when they come in contact with those atoms. So they're very ionizing. However, what we realize with alpha particles is that they're not able to travel very far, right? They're not able to travel very far in air. They're only able to travel about a few centimeters in air, right? And they are blocked by, what can we use to block alpha particles?
Either paper or skin, sir.
Right, a thin sheet of paper, right? So alpha particles are blocked by a thin sheet of paper. So you can just imagine your skin. If they were to come in contact with your skin, they won't be able to penetrate your skin. So they wouldn't really cause much damage to the tissue, human tissue. Everybody accept that so far?
Oh, sir, it's gamma wave,
Right.
the most
Let's kind
dangerous.
of go to them slowly. So beta now, we know beta particles, right? They're not very ionizing in terms of comparison to alpha particles. However, they are able to travel a little further in air, right? Up to about a meter or so in air, right? So alpha particles are able to travel a little further in air. However, right, they can be blocked by what?
A thin sheet of aluminum metal.
Right, a thin sheet of aluminum. So we can stop beta particles using a thin sheet of aluminum, right? Now, we have the gamma, right? Now, the gamma waves, these are not very ionizing, right? However, right, they have high energy and they're able to travel much further in air. They can travel several meters in air. That's the gamma. They can travel several meters in air. So what we're going to see now is that these will be able to penetrate human tissue, right? Because they could actually even pass straight through the body. And in doing so now, they will now affect different cells and ultimately affect human tissues. You with me?
Yes, sir.
Right? And also, in terms of radiotherapy, right? Radiotherapy involves the use of gamma rays, right? In which affected tissues are, what can I say now? They are targeted with a beam of, a concentrated beam of gamma waves to help to get rid of any cancerous growth or cancerous tissues, right? And oftentimes, I mean, you know, healthy tissues are damaged in that process. And that is why, you know, most times when persons go through that kind of therapy, they usually, you know, have hair loss in terms of, you know, they lose the hair on their head. And, you know, they usually, you know, lose muscle tissue. So they look weak and things like that, right? Because of the effects of the gamma waves or the gamma radiation, okay? So most dangerous is going to be the gamma rays, okay? Cool?
Oh, well, I thought he was asking out of the two.
No, because I said two types, you know, so I mean, you could have listed gamma here. If that said that, okay, from the above listed emissions, which is the most dangerous? In that case, no, you could relate it to what was mentioned right here. Okay?
Yes, sir.
All right? So now, let's continue. So next one now is also another radioactive question. So let's go through this one. So it says, an atom consists of 3 types of particles, protons, neutrons, and electrons. Complete the following table to show the charge of each particle. So the proton, what do we know about its charge?
Positive.
It's positive.
Okay,
Right.
positive.
1.
Positive, right? And we could say, okay, +1, like that. Neutron,
Neutral.
Neutral.
right? Neutral. So we put 0. And electron,
Negative.
negative, right? Which is -1. Now, yes, somebody said, sir?
Yes, sir. I have a question
Go ahead.
pertaining to the graph.
Okay.
Sir, should it be instead of days, should it be disintegration per se?
For what?
Graph.
Oh, you're talking about the yes. This one right here, yes. This one should be 5 disintegrations per second. You're right about that.
Okay, sir.
Right?
Oh, I was wondering about
Yes,
that, you know.
just because it's the activity, for real. Disintegrations per second. Or you could have said S-1, right? So that's why, I mean, these things, we have to pay close attention to them in terms of when we're working these questions. So it's because, have to be going back and forth to the graph, so it kind of, I lost track of what I was actually measuring for. But good point. All right, so that's cool now?
Yes, sir.
All right. So now, next one down the line says that for the element radium, determine the number of each of the 3 particles referred to in A, which are our protons, neutrons, and electrons. Now, how can we determine the number of protons in this atom of radium?
Should it be equal to the atomic number?
Right? So the number of protons is equal to the atomic number. What's the atomic number in this case?
88.
88, right? So remember, the atomic number is the one at the bottom. So number of protons we say it'd be 88 protons. What about neutrons?
So minus the atomic number from the mass number.
Right? So remember our nuclide notation, let us say X,
Is equal to
right? And
A
A,
is equal to C plus N.
right? Z plus N, where Z is our atomic number, right? This is the mass number, and this is our number of neutrons. So now we can say that N is equal to A minus Z, which is A is 226, 26 minus Z, which is 88, and this is
138.
138 neutrons. Cool? Then our number of electrons now.
88.
Why was it 88?
So it's the same thing as the proton.
Okay? Alright? Why? Huh? Why would it be the same number of protons, number of
Because
electrons?
this number of existence of charges inside of a nucleus. So
Repeat?
it is the number of charges inside of a nucleus.
No, but we're talking about the electrons. Why are we saying that the number of electrons is the same as the number of protons?
To equalize the charge of the atom.
Repeat? Oh, okay. Say that again?
Equalize the charge of the protons in the nucleus.
Right, so to neutralize the charge of the protons in the nucleus. So remember, atoms are normally neutral and stable. Neutral meaning that they have same amount of positive as there are negative charges. So the number of positive charges and number of negative charges are usually equal. So you will find that most times the atom is neutral, right? So what we're going to say now in this case is that we're going to have also 88 electrons. So these are things that, the examiner will often ask. They might ask, I've seen them ask a question where they say, okay, why is the atom normally stable and neutral? Now, in terms of its stability now, you have to speak about, okay, the number of protons and neutrons inside the nucleus, right? And in terms of its neutrality now, we have to talk about, okay, number of protons and the number of electrons. Cool?
Yes, sir.
Right? Now it says state one similarity and one difference between the isotopes and element. What's the similarity between isotopes of an element?
Sure, they have the same number of protons.
Right? It's the same number of protons, or we could say what?
Atomic number.
Right? Or the same atomic number. Sorry. Same atomic number. Right? And difference?
Different number of neutrons.
Right? So different number of neutrons. And as a result of those different number of neutrons, we're going to have what?
Different mass number.
Right? Different mass number. So we want to be able to relate isotopes to these characteristics. Right? So an isotope is different forms of an element that will have the same atomic number but a different mass number. All right? So now, let's go again. So here they asked us to define the term half-life. So what are we going to say about half-life here?
Sir, half-life is the time taken for the activity or mass of a radioactive substance to decay in half.
Right? Taken for the mass or activity of a radioactive substance to decay, let me use that word, as you say, decay or to reduce to half its previous
Original value.
right, previous value, right? So that's half-life, right? That's half-life. And also, since we're talking about radioactivity, we also want to be familiar with what exactly is radioactivity or radioactive decay, right? What's radioactivity? What could we say about radioactivity? What is it? What's radioactivity? Anybody know?
What is radioactivity?
Yes.
Radioactivity is a spontaneous process where
The act of emitting
Hold
radiation
on a second.
spontaneously.
Hold on a second. Todd, let me hear from Todd. Continue, Todd. Todd, continue.
I said radioactivity is a spontaneous process where a substance produces half its life.
Okay. All right. Okay. It started out, kind of good, but
So I have one.
hold on. Let's not, try to be too
Yeah,
quick with.
it's a spontaneous process where radioactive decay takes place.
Right. Yes, but as I said, you started out good because you mentioned that okay, it's a spontaneous process, right? And being spontaneous would simply indicate what?
It is random, sir.
Random.
Right, it's random, right? So we want to be able to appreciate that radioactivity or random decay, right? Or radioactive decay is a random process, right? Now, when that random process occurs, right, what you have to also be aware of is that it takes place inside the nucleus, and it is due to the state or the conditions inside the nucleus. So it will occur when we say that an atom or the nucleus of an atom is said to be unstable, right? So what we can say, and everybody else wanted to add in something else. I heard, I think it was Janelle, you were the one who were adding something to.
Oh, Andre is the one that was adding.
Oh, who?
Andre.
Andre, yes, go ahead.
Oh, sir, I was saying that radioactivity is not the um, of emitting radiation spontaneously.
Okay, the act of emitting radiation, spontaneous. Okay, so we now mentioning the fact that okay, it involves the emission of radiation. And we're gonna be talking about that also. Shanice, what else were you saying?
I have one. Radioactivity. This is the emission of ionizing radiation or particles caused by spontaneous disintegration of atomic nuclei.
Okay, good. So we can put it all together now where we say that okay, radioactivity, it's the random, right, disintegration of an unstable atomic nucleus, right? It's the spontaneous or the random disintegration. So in other words, the nucleus is actually breaking down. And how it breaks down is that it will emit different types of radioactive emissions. So it will emit either alpha, beta, or gamma waves. So what we can say now is that radioactivity is just the random disintegration of an unstable atomic nuclei with the release of either an alpha particle, a beta particle, or just gamma waves. Okay? Or gamma rays. Okay? Yes, please?
Yes, so you could repeat it.
It's the random disintegration of an unstable atomic nucleus, right, resulting in the release of an alpha, beta particle, or gamma rays. Okay? So we have to mention things, and again, remember, it is solely due to what's going on inside the nucleus of the atom. All right? Anybody have any question?
No, sir.
Okay? All right, so let's continue again then. So next one now says that the element thorium has a half-life of 24 days and undergoes beta decay. Calculate the time it will take for 10 grams of thorium to decay to 1.25 grams. So how do we do this question now? How do we do this question?
We'll use the arrow method and find the time it takes to decay from 10 grams to 1.5 grams.
1.25, right? So we could say initially it's going to be 10 grams, so we could start with 10. Then after one half-life, the mass will be what?
5,
5 grams.
Right? 5. Then after one more half-life, it's going to be
2.5,
2.5,
2.5. Then after one more,
1.25.
2.25, right? So here now we're going to have 1, 2, 3 half-lives. So to find the time it takes to go from 10 grams to 1.25, we're going to say, okay, since we had 3 half-lives and each half-life is 24 days, we're going to see that our time then now will be equal to the number of half-lives, which is 3, multiplied by the time for one half-life, which is 24 days, yes?
yes, sir.
Yes, sir.
So we say 3 times 24 is
72.
72
Yes, sir.
days. All right, so that's how we would work a question like this. All right, everybody okay with this?
Yes, sir.
All right. Can scroll again?
Yes, sir.
All right. So now that's that. All right. So now let's look at this question now on waves. So it says distinguish between transverse and longitudinal waves. What can we say?
So transverse waves are perpendicular.
Okay.
So I'm on the right here.
Sort
Longitudinal
of.
waves are perpendicular.
Repeat.
So which one of them is perpendicular? Is it transverse or longitudinal?
Well, it's not so much the wave. Hold on a second. It's not so much the wave is perpendicular or otherwise. When we're talking about waves, we have to relate it to the movement of the particles of the medium. Okay?
Okay.
So we have to state, okay, are the particles perpendicular or otherwise. So,
So it is perpendicular.
Mattis, hold on, try again, Mattis. Let me put it together.
So what, the same waves?
Yeah, man, same transverse wave. Let me put it together.
Oh, sorry. So the transverse waves, the particles are perpendicular.
Right, the particles are moving.
Yeah.
Right? So transverse waves are waves in which the particles, we're going to say vibrate, and you said what, perpendicular?
Yeah, to the propagation.
Okay, good, because I was going to ask you perpendicular to what? Perpendicular to the direction, right? I would say of, based on what you said, of propagation. So in other words, the direction of the wave, right? So that's transverse wave.
Energy transfer.
Or the energy transfer, right? So different ways we can define the transverse wave, but again, we have to make mention of the fact that, okay, the particles are vibrating perpendicular to wherever the wave is going, all right? So longitudinal, now what we say about these now?
Excuse me, sir. So what's
Yes?
the word after perpendicular to the?
To direction of propagation,
Thank you, sir.
okay? Longitudinal
Parallel.
waves, what we say about these now?
So just the
Right?
opposite.
Parallel.
Right, are waves which the particles vibrate parallel to the direction, and I'm going to use the same word as we did up top, direction of propagation. Right, and again, remember when we talk about the particles, we're talking about the particles of the medium. Okay? So just want to be clear on that. Next one now says, state one example of transverse and longitudinal wave. What can we see?
Transverse.
Go ahead.
One example of transverse is electromagnetic.
Right, so EM waves,
And water wave.
right, water waves. We could get another example. Anybody have any other examples?
Light wave, sir.
Well, light is at EM, so that would kind of blanket.
Sir, all water waves perpendicular.
Because remember, if you have a container like this, let us say you have water here, you drop a stone right here, right? The stone, the waves are going to ripple out, and the wave is going to be traveling that way, away from the stone. So the particles, which is the water, move up and down. So think about like you have a boat and the water. The boat is going to be going up and down because the particles of the wave are going up and down, but the wave is traveling perpendicular to that up and down motion.
All right.
Okay?
Thanks.
Next one now is longitudinal wave.
So sound.
Example.
Sound.
Sound.
Seismic.
Right? Seismic.
The slinky.
Right? Right, so slinky, yes, so we can use a slinky. Right, slinky spring. And again, it all depends on how we oscillate the particles of the slinky. Right, so you can definitely include a slinky spring. Now, in the wave equation, velocity, frequency, and wavelength are related. What's that equation?
So velocity equal frequency times wavelength.
Right, so V is equal to F lambda for a single mark. So we want to be familiar with this formula since we're looking at waves. Next one now says that a wave motion has a frequency of 10 Hertz and a wavelength of 250 meters. Calculate the speed of the wave. So we're going to be able to use our formula for this one, correct?
Yes, sir.
So we say V is equal to F lambda. That's the first thing we do. And we say F now is 10 Hertz and lambda is 250 meters. So this works out to be
Meters per second.
meters per second, just like that. All right, then continuing down, we're given this diagram right here, and it says we're to indicate and figure for the amplitude of the wave. So to do that now, we're going to simply show using an arrow. So we must use an arrow, right? Oh, they didn't. But they say indicate the amplitude of the wave. So to do that, what's the amplitude quickly?
0.5 millimeters.
No, not,
But you
that's the
have to
definition. What's the
find it.
definition for the amplitude? How do we define amplitude?
The maximum displacement of a wave from its resting position.
Right? So the maximum displacement from the rest position. So the rest position in this case would be our horizontal line right here, and the maximum displacement would be here. So we need to show that, okay, the amplitude will be measured from the maximum displacement straight down to our initial or our...
So your mouse now move. Oh, okay.
Right, yeah, is that thing with this. It doesn't, but it can see the writing though.
Yeah, yes, sir. I can see right. I thought you were moving the mouse to show us.
Yeah, I was moving it, but it's just not showing. So this is the maximum, this maximum highest point. This is our rest point right here. So we'll show that the amplitude is measured between these 2 points right there. Alright? Next now it says now we're to state the amplitude in meters. So here now, we have our amplitude would be 0.5 millimeters, but the examiner wanted it in meters.
So you have
So we're gonna add,
convert. You divide by 1,000.
right, so 0.5 and we divide this by 1,000 and we get what?
0.00505.
Meters. Alright, good so far?
So can you go back to that again, please?
Yes, so based on the diagram, the amplitude would be 0.5 millimeters. See that?
Yes, sir.
But the examiner wants the amplitude in meters.
Okay.
So we record the value. Huh?
Oh no, man, I get it. Thanks.
Okay, cool. So we get 0.05 millimeters. Sorry, meters, my bad, sorry. Period now in second. What's the definition for the period?
Time taken for
Time it takes to complete it.
Time taken for one oscillation to be completed.
Yes,
Right?
sir.
So how do we determine one oscillation from this, from a graph, a wave plane?
Well, so when it makes a S shape,
Okay, so when it makes this S-looking shape, would represent one wave from right there, come all the way around to make that S shape would be one wavelength. So we need to know the time it takes to make this S shape. What's the time it takes to make this S shape?
4 meters per second.
4 meters per
Millimeters.
second?
Yes, meters.
4 meters per second?
Yes, yes.
We all agree, meters per second?
Per milliseconds.
No, sir, you have to get it in seconds, sir.
But hold on a second though, because I kind of see where the challenge was. So notice we're given the unit, right?
Milliseconds, sorry.
Milliseconds. So this is milliseconds.
Okay,
Remember,
I
we're
can
talking
convert.
about time. So this is 4 milliseconds. Right? 4 milliseconds. Right? And we convert it to seconds by dividing by 1,000.
Yes, sir.
And we'll get, this would be what?
0.000.
Seconds. Alright? Next thing now, we
Sir,
say we
why
need to find the
1,000?
why we divide by 1,000, because we're converting milliseconds to seconds. And milli is 10 to the minus 3. So we divide by 1,000 to convert to seconds. Okay? Yes? No?
Yes, sir.
Right. Next now, they say we need to find the frequency. How do we define the frequency of a wave?
So you just divide it by 1. 1 over the time.
So 1 over the period.
Right, okay? But first, let's define what is the frequency.
Sir, is it the number of waves that pass a fixed point?
Number of waves. Repeat?
So it's the number of waves that pass a fixed point. Pass a fixed point.
Okay, number of waves passing through a fixed point. Okay? Okay. I get what you're saying, but there's something missing from that definition. So I say in the message or the chat, number of cycles completed in 1 second, right? So to your statement, Sarah, if we had said that, okay, is the number of waves that pass a fixed point in 1 second, right? We could use that to define the frequency, because the frequency tells us how many cycles are completed in 1 second. So you have to indicate that, okay, there's a time, because think about it, frequency is how often something happens, right? So the frequency by definition is the number of oscillations or the number of wave cycles completed in 1 second. So now, to find the frequency now, there's a relationship between the frequency and the period. So we know that the frequency f is equal to
1 over t.
1 over t, where t is the
Period.
period, right? So we're going to say 1 divided by 0.004 seconds, and this works out to be
250 hertz, sir.
hertz, right? So 250 hertz, okay?
Yes, sir.
Now it says state one property of an electromagnetic wave. What do we know about AM waves?
It
It travels the
propagates
speed of light.
So they travel the speed of light, which is
378 meters per second.
3 times 10 to the 8 meters per second. Anything else you know about
It propagates in a vacuum.
okay, they can travel in a vacuum. Anything else?
Sir, they are transverse waves.
Right, so transverse waves by nature. Anything else? Anything else? Electromagnetic. Anything else? Anything else? Yes, no? Yes, no, anything else?
Sir, I don't remember it.
All right, look at the word again. Electromagnetic.
It is both electric and magnetic.
Right? It has both an electric component or an electric field and a magnetic field. So it has both an electric field and a magnetic field. All right? Now, it says we're to explain what is meant by the term electrical resistance. What are we going to say about this one?
The ability of a component to slow the movement of electrons.
Okay. So repeat for me again.
The ability of a component to slow the movement of electrons.
Okay, so the ability of a component to slow the movement of electrons. So when we talk about electrical resistance, we have to be aware that it is, as you mentioned, it's some ability, right, to oppose the movement of, what did you say? Slow the movement of?
Electrons.
Electrons, right? So we have to be aware that, okay, electrical resistance has to do with the... Hold on a second, hold on, let's hold it out for a second. It's going to oppose the movement of electrons. Now, remember, the movement of electrons results in the flow of what?
Current.
An electric current, right? So when electrons move, we get an electric current. So electrical resistance is just the opposition to the flow of electric current, or we could say the flow of electrons. So Todd, let me hear what you say.
I was saying electrical resistance sounds like what you say now, an insulator.
An insulator will have a very high electrical resistance. Okay?
Sir, please can you repeat what you just said?
Yes, I'm going to put it down on screen. All right? So electrical resistance, we could say that, okay, this is it's some property So we could say that this is the property of a material which opposes, or as you say, it slows down or it limits the flow of electrons, right? And again, remember, as I said, when electrons flow, we get an electric current. Okay?
Sorry, sir. So what was the meaning for frequency again?
Frequency is the number of oscillations completed in 1 second. Or you could say number of wave cycles completed in 1 second.
Thank you, sir.
Okay? All right, so we're okay with this definition for electrical resistance?
1 second, sir.
Kara?
Yes, sir.
Right, all is well?
Yes, sir.
All right. Chrisanne?
Yes, sir.
You okay?
Yes, sir.
Okay, good. All right, so let's scroll on a little. So now, next thing says that we're to complete table 2 to provide information regarding electrical meters. So we're going to be discussing this in detail right now. Alia?
Yes, sir.
Yes, you following along?
Yes, sir.
Okay, any questions so far?
No, sir.
Okay, all right, so it says now table 2, complete table 2 to provide information regarding electrical meters. So we have our ammeter and we have our voltmeter. Now, how do we connect an ammeter in a circuit? Do we connect it in series or do we connect it in parallel?
Series.
Series?
Series, sir.
Okay, so ammeter is always connected in series, right? And in terms of the resistance of an ammeter, does an ammeter has a high resistance or a low resistance?
Sir, low. Low, sir.
Why low? Why low?
Sorry, sir. High resistance. Sir,
All right,
it's...
why high? Wait a second, let me hear from Todd. Where you say high, Todd?
No, sir. Isaac, you say high.
No, man, I said Todd. Yeah, Todd, where you say high resistance? All right, who says?
You know,
Oh, yeah, go ahead.
for low resistance, it actually checking how much current is flowing through that resistor. So I would say low.
Okay.
Yeah.
And why low?
Because it's accumulating for the current that's moving through a resistor.
Okay, all right, so remember, the ammeter, it is used to measure current flowing in a circuit. I mean, yes, we can use it to measure the current in a resistor, but we just have to be clear in terms of why we use an ammeter. An ammeter is used to measure the current flowing in a circuit, right? Now we place it in series, yes, and we're saying that theoretically, the ammeter has a very low resistance, right? Theoretically, we say that it is infinitely low, so it's almost zero, right? So it's a very low resistance, and the reason why we want the resistance to be low, because remember, resistance, electrical resistance, is an opposition to the flow of electrons, which is electric current. Now, what we're saying now is that if we have a low resistance in the ammeter, when you connect it in series, it's not going to cause any, or it's not going to affect the amount of current flowing in the circuit. So we don't want to be using a device that in itself is causing us to get an error, because that wouldn't make much sense. You follow what I'm saying?
Yes, sir.
So we want it to have a very low resistance so it doesn't affect the current in the circuit. So, and I mean, it will help us in terms of answering this one. So we're going to say we're going to have a low resistance, right? And this is to ensure the ammeter does not reduce the current flowing in the circuit, right? And we could really say affect, right? To reduce or to affect the current flowing in the circuit, right? Good so far? That's good?
So you could say interfere too? Not
Yeah,
interfere.
interfere, yes.
Or
Yes, yes. Right. So what about the voltmeter now? How we connect the voltmeter?
parallel.
Parallel, right? And what about the resistance? Is it high or low?
Sure, high.
High, right? Why high?
Sir, so that the current doesn't go towards the voltmeter.
Right, so to ensure no current flows through THRUGH, the voltmeter. So when you connect it in parallel, because of the resistance so high, it's usually infinitely high, right? So no current theoretically will flow through the voltmeter. Okay? Question? Okay.
So you can go to the screenshot of this.
Yes. Right? Have it? Have it now?
Go on.
You said go ahead?
Go on.
Okay. Anisha, any question from
I
you?
just have it.
So please can you explain why you put the reason for the voltmeter? Like why is that the answer?
Why is it parallel?
No sir, like to ensure no current flows through the
Flows through the voltmeter. Okay, all right, so let me just do a demonstration. So let's say we have a circuit like this. Let's say we have that. Let's say we have a device here and there's a current flow, right? And we want to know, okay, what's the potential difference across this device? We're going to connect our ammeter like this.
Sir, voltmeter.
Voltmeter, right? Ammeter is always connected in series. So we're connected to a voltmeter like this, right? Now a voltmeter will be used to measure the potential difference across this device right here. So it's going to measure the potential right here, and the potential right here is going to determine the difference, and it's going to give you a reading. Now what we're saying now is that when we connect to a voltmeter, right, because it is connected across this component right here, we don't want any current to be flowing here. We don't want any current to be flowing here, so we're going to put an X right there. Let me go back a bit. So we don't want any current flowing through our voltmeter, right? So we'll make the resistance of this very high. And remember, resistance is the opposition to the flow of electrons. So if we make this resistance very high, no current theoretically will be flowing through the voltmeter. All the current will go through this device right here. Cool?
Yes sir.
Right, so that's why we have the voltmeter having a very high resistance. Yes?
Yes, thank you sir.
Okay, good.
Sir, and
Alright,
can
so
you demonstrate
continue. Go ahead.
Sorry. So can you demonstrate the ammeter one as well, please?
Ammeter, alright, so same idea. So we have our ammeter here. Alright, and again, it's in series. That is why we place it like that, in series. And it's going to measure the current flowing in the entire circuit and also the current flowing through this resistor. Now, if we had used a very high resistance for this ammeter, it would actually cause little current to flow in the circuit. So even though we're trying to use it to measure current, it's causing the current that is flowing to be less or to be little or to be small. And we don't want that. So we allow this to be almost 0 ohm, right? To be its resistance, so no current will actually, theoretically speaking, what we say is that there is no potential difference across the ammeter because the resistance is 0. So again, the basic premise is that we want the resistance of the ammeter to be as small as possible so that it doesn't cause any, or it doesn't actually affect or reduce the current flowing in the circuit itself, okay?
Oh, so the circuit will be clear, open, sir, when it ammeter is checking.
No, man, no. It's going to be closed because the resistance is 0. So it's just like you have a piece of wire where the ammeter is. So it does not cause any reduction in the current flowing. If we had used, think about this thought, if we had used a very large resistance, now let us say 1,000 ohms or 10,000 ohms, because it's usually like 100k, well, in terms of the voltmeter that is. Let us say this is like 10 mega ohm, right? A 10 mega ohm resistor in series. What that will do now, that will actually now cause probably no current to be flowing. Let's say this is probably a 2 volts. So you're going to have no current, and we can actually show it. Let us say we calculate the current. So we're going to say I is equal to what? How do we calculate current? Using voltage and resistance. Repeat?
I is equal to V by R.
No, man, we're trying to find current. So I is equal to what?
V over R.
Right? V over R. So V over R, so V is 2 volts, so we say 2 volts divided by 10 mega ohm. This is like 10 times 10. Mega is 6, so 10 to the 6 ohms. So if we do this calculation, we're going to get something like 2 times 10 to the minus 6, maybe, something like that. Check it and let me know. I'll just kind of estimate this. What's that going to be? Oh, it's minus 7, right? Let's do the real calculation. So it's minus 7 ohm. I mean, not ohms. It's current, so it's going to be
7,
amperes.
sir.
Right? Amperes. So 2 times 10 to the minus 7 amperes. So this is like 20 milliamps. No, not million. 20 microamps. Right? 20 microamps of current is flowing. So a very small amount of current due to us having a 10 ohm resistor in the circuit. And as a matter of fact, we didn't even consider the resistance of this. So it's probably going to be lower than what we calculate right here. But again, this is just to quickly demonstrate to us that, okay, we don't want to use a large resistor in series, right? Because it's going to cause little current to flow in the circuit, and we don't want that. So we're going to use, as I said, a resistance, or sorry, an ammeter having a resistance of 0 ohm. So is that good?
Yes, sir.
Right, Corregina?
Yes, sir.
Right? Can continue now?
Yes, sir. Thank you.
Right? Yes, got it, no problem. All right, so next thing now says calculate the reading on each of the meters shown in figure 2 when the switch is closed. So we're considering that our switch right here is closed. So when we close the switch, what's going to happen to the circuit?
Electricity will be able to run for it.
Right? So electricity will flow through our circuit. So this circuit now will be electrified or it will be powered, right? So we're going to have electricity flowing in the circuit. So this is we need to find what? The reading on the meters. So the meters that we're seeing right here, what are these meters?
Ammeters.
Ammeters, right? So we have one ammeter right here, A1, we have another one, A2. So therefore now the examiner
Ammeter,
wants us
sir.
to find what? Examiner wants us to find what?
Ammeter 1.
The ammeter between
Ammeter.
that resistor in the middle.
Right? So we want to find out the reading on this ammeter. The reading on this ammeter. Now the reading on this ammeter will be what quantity are we going to be measuring with this ammeter right here? What physical quantity?
Ohms.
Current.
Current. Ammeter is used to
Oh,
measure
current,
current.
current, sir.
Current. Right? Current. So we're going to use this to measure the current flowing, right? Here, well, let me put an arrow. The current flowing here and the current flowing here. We're going to use our ammeters to do that. Now, let's just kind of analyze what's going on now. So let us say ammeter A1. Ammeter A1, which is this one right here, will be able to, or will be measuring the current coming from where? Ammeter A1 measures the current coming from where?
On the battery, sir.
From the battery, right? So A1 measures the current from the battery, right? And when the current from A1 flows, when the current from the battery flows through A1, where does it go?
It's A2, sir.
It only goes to A2?
Throughout the circuit.
No, sir, it splits
Throughout
and
the
goes to
circuit?
Yes.
Continue, Sarah?
You're welcome.
What you said, Sarah?
I was saying that it splits. When it splits and go to the resistance and the that's no bother, sir.
Okay. But ultimately, what we see is that the current will flow from the battery and it will go to the rest of the circuit, right? We could say that, yes?
Yes, sir.
So it flows from the battery and goes to the entire circuit. So this current that is coming from the battery, this current I, we can say that, okay, this is the total current that's going to flow in the circuit, right?
Yeah.
So that's the total current. So let us say we start with A1 first. So in this case now, we want to find the total current. Let us say IT. So the total current in the circuit will be equal to what?
So velocity over resistance.
Velocity?
Voltage.
Voltage, right? So we're going to have V over R. But V will be the V of what?
12 volts.
12 volts, which is from the battery.
On the
so we
battery,
could say,
sir.
let's say
Sir.
VT. Yes?
Sir, this session is recorded, right?
Yeah, man, it is.
All right, thanks, sir. Can I step off a little bit, sir? I'll fall back.
Okay.
All right.
So we're going to have VT, which is the total voltage of the battery, or we could say more appropriately, the EMF of the battery. Yes?
Yes, sir.
Right? And we're going to divide that by R, where R would represent the resistance of what?
2 amps.
Circuit.
Yes.
The circuit. So the current flowing through the entire circuit is due to the resistance of the entire circuit. So we're going to say VT over RT. So what's VT? We know that to be 12 volts, not true?
Yes, sir.
But what's RT?
We have to find that, sir.
Okay, we have to find that. So let's see if we can work on find that. So to find that now, find the total resistance, we have to look at our circuit and say, okay, what circuit is this?
Parallel.
Parallel circuit?
Series.
Parallel.
Sir, parallel and series.
Huh? I'm in parallel, I'm in
It
series.
is a series circuit.
There's parallel.
Series. Okay, so I hear some say series, some say parallel. So let's determine. Let's determine it. All right. So let me see if somebody in the chat. Series parallel. Okay. All right. So let's look. So let us say when the current flows from the battery, like this, represented by this blue line, when it reaches at this junction here, what we're gonna see is that the current. What will happen to the current when it reaches this junction, Sarah?
It flows through one end.
Sarah?
Sir?
What happens to the current when it reaches at this junction represented by this dot right here?
Sir, will it split?
It's going to split, right? So once the current splits, that tells us that we have a parallel network right here, or a parallel branch. There we could say that, parallel branch, right? So the current will split, some will go down here, and the rest will continue here. So now, when the current continues right here, it's going to go through the 2 ohm resistor, right? And then it's going to continue, and it's going to go through the 4 ohm resistor. So now, what we can see now is that, okay, wherever the current split will always be a parallel network. Can we agree to that?
Yes, sir.
Right? So right here, let me put it P, parallel. Right here will be our parallel network. Now when the current continues right here, it flows through R1 and then it continues along the same path and flow through, well, it flows through the 2 ohm resistor and continues along the same path and flows through the 4 ohm resistor. So we see that the path that the current takes after it would have split right here is going to be a single path. So therefore the 2 ohm resistor and the 4 ohm resistor, this 2 ohm resistor and this 4 ohm resistor, we can say that they are connected how?
In series to each other.
In series. So what we see now is that we have these 2 resistors, let us say, these 2, let me just label them. Let us say this is R1, R2, and R3. So what we can say is that R2 and R3 are in series, right? But R1 is in parallel with R2 and R3. Okay? So now, what we have to do now is we have to do some sort of a simplification of this circuit. Got that? We have to do some
Yes, sir.
simplification.
So that means 2 ohms and 4 ohms is parallel. This is a parallel, so you could work it too with 1 over RT.
All right, use R1 and R2 and R3 when you're talking, so we can get clarity. So hold on a second. Let me just hear what Shanice is saying, please. Shanice, what are you saying?
Yeah, I was saying, right? I was studying to work for like the parallel first, like the 2 that is parallel, like the 2 ohms and the 4 ohms. I was planning.
All right, because hold on a second, Shanice. Because we have two 2 ohm resistors. If you say 2 ohm, I'm not sure exactly which one. So use the labels that I would have given right here: R1, R2, and R3.
Okay.
So what are you saying now?
So I have to add up all of them.
All right, no, hold on. You were saying something about series and parallel. I just want us to be clear on that because maybe somebody else, having a similar challenge or a similar question. So let me hear what you have to say.
No, sir. All I was just saying is if the 2 ohms and the 4 ohms is really parallel.
All right. So let me go over it once more. Let me go over it once more. So again, if we monitor the path of current, when the current, let me use a different color. Let me erase these so we can start from scratch. So what we're saying is that when the current, let me use this one. When the current flows from the battery, it's going to continue through A1. When it reaches at this point, right, right here, the current splits. Some will go here, the rest will continue there. Once the current splits, it simply means then that the junction right here creates a parallel junction, right? So these 2 resistors, so in other words, this resistor R1 will be connected parallel to R2 and R3. Okay?
So we could work.
Cool?
Okay.
Now hold on, let's just fully appreciate the circuit before we can say, okay, where we're going to go next. All right? So we need to know the destination, yes, and we need to know, okay, where are the, just like the Dora show, we have to know, okay, where we go next, and so on. So let's just get clarity on that. So we just said that, okay, we have this resistor right here, R1, be connected parallel to R2 and R3. Then now, we're saying now that the current is going to flow here. It's going to go through R2 and continue and go down and flow through R3. And what we see now is that when the current flows through R2 and R3, the path taken is just one single path. Okay? Yes? I need some responses. What's going on?
Yes.
What?
Yes, sir.
So R2 and R3 are in series, right? And they are connected parallel to R1. Okay? Cool?
Yes, sir.
So now, in order to simplify this circuit right here, what we would have to do is we would have to take care of the series resistors, right? Because we cannot work out the parallel resistors unless we would have resolved or would have found the equivalent resistance of these two resistors in series. So let us say we do that now. So we're going to say, okay, the equivalent resistance in series. So let us say series. So to find the equivalent resistance in series, we can say R EQ is equal to R2 plus R3. So we say R2 plus R3, which works out to be 2 ohms plus 4 ohms. And this would be 6 ohms, right? So that's our series. So that's for the two resistors in series. So now, instead of having these two resistors right here, we can just replace them with a single resistor that will be in parallel to this one right here. Following so far?
Yes, sir.
So then now, let me just sketch a new circuit. So we're going to have our battery here, say like that. We have our ammeter here. We're going to have the R1 here, ammeter here. And then we're going to have, instead of two resistors, we're just going to have a single resistor. Right? That will be parallel to this one. Everybody okay with that?
Yes, sir.
So now, this will be R1 as we label it, this will be REQ. So now, because we have two resistors in parallel now, we can say, okay, let's find the total resistance of the circuit. So we're going to say now that RT, let's put it right here, RT, well, since it's parallel resistors, let us use the general formula. So we're going to say 1 over RT is equal to what?
Is equal to 1 over R1 plus 1 over R4.
Right, or REQ, let's call it REQ. Right?
Sir.
Cool?
Sir.
Somebody said, sir?
But sir,
Is there a question?
this is not
No, hold on, wait a second,
other equation.
Hold on. Kavon, you were asking.
Yes, I just want to know what REQ stands for.
Oh, REQ is just the equivalent resistance of this R2 and this R3 in series.
Alright.
Okay? So I heard somebody mention R4. We could call it R4 as well, but you know, I prefer to use REQ, right? Because it's equivalent resistance. Todd, you were asking me a question. Go ahead.
Sir, well, I'm saying
Go
that
ahead.
if we have two resistors in a parallel, we don't use the other equation where
Which
the
is?
sum, we'll find the sum and the product of the resistors.
Yeah, I
Yes,
was
yes,
saying that too.
yes, I was going to use that, but remember, you will notice that I will use, in this case, I'm using the general formula because I want persons to be aware of, okay, how to actually utilize the equation if it is that you're not given two resistors. Because you're not always will be given two resistors, you know. So you just have to be aware of, okay, how to actually use this. Yes, we could use that one, and as I said, I was going to use that, but in the back of my mind, I said, you know, let me utilize this one. So persons can be aware of, you know, how to manage the fraction. So we're going to have R1. R1 is the 2 ohm. So we say 2 ohm right here. And the equivalent resistance in series, well, in parallel in this case, was 1 over 6 ohm. That's good so far? Everybody following that? Everybody following that? So we say LCM right here. What's the LCM of 2 and
6.
12.
right? So 2 into 6. Well, I don't need to put, let me not put the ohm right here, just to make the calculation a little easier. So we say 2 into 6 goes 3 times, so we have 3 times 1 is 3, plus 6 into 1 goes 1 times, so we're going to have 1 right there. So 1 upon RT is going to be equal to 4 over 6. And since we're trying to find RT, we're going to reciprocate both. So we're going to get RT is equal to reciprocate this, we get 6 over 4, which is the same thing as what?
1.5 ohms.
0.5 ohms. So that would be our total resistance. Then now, once you know the total resistance, we can go ahead and actually find the current flowing in the entire circuit. So IT is equal to VT over RT. So now, VT would be the 12 volts, and RT is going to be this value right here, which is 1.5 ohms. This value works out to be
8 amp.
right, 8 amperes. Okay?
But sir, I did it the other way
Yes.
and I got a different value.
Did it other way meaning?
I used the sum over the product and I got the
No. See,
1.32.
no. Wait. That's where you're kind of going at it wrong now. So in parallel, two resistors in parallel, you take the product over the sum, right? For two resistors in parallel,
Oh, right.
right? It's product over sum, right? Product over sum. Cargina?
Yes, and for that one I got a different value.
Different value for what?
So the total resistance.
All right, what's the product? What two resistors are you multiplying?
The product would be the two ohms multiplied by 4 ohms divided by
No.
2 ohms add by 4 ohms.
It's 2 ohms multiplied by this one right here, REQ, which is 6 ohm.
Oh, 6. Oh,
Yes, Cargina, you had a question?
No, sir.
Okay. All right, now we need to find the reading on A2. So let's talk about that now. So we need to find the reading on A2. So we're saying now that we're going to have 8 amperes coming from the battery. So we have 8 amperes flowing from the battery. When the 8 ampere comes right here, it's going to split. Right? It's going to split. Now, for this question now, we can consider that, okay, let me just use some circles. We can consider that this resistor, right, I circle the ammeter a part of it because again the ammeter will have 0 resistance. So this resistor R1 and these two resistors, how this looking to you guys? Is this looking okay to you guys, the diagrams? Or we're coloring up the diagrams? Talk to me, if you guys can follow what we're saying. Yes, no?
Yes, sir.
Right. Anybody having difficulties, let me know. All right, okay. So we're saying that this resistor R1 is connected parallel with R2 and R3. So let me just consider redrawing the circuit in a sense. So let us say we have our battery here. I'm just going to draw it without the ammeters, right? We have one resistor here, which would be the R1, and our other two resistors, let me draw them like this, so you guys can probably appreciate it a little better. Seeing it now? How does this look to you guys?
look great, sir.
Right? So this is really what our circuit is like. So we have R1 right here, R2, and R3. So what I'm saying is that R1 is connected parallel to R2 and R3. Yes?
Yes.
Right? And the battery was providing 12 volts to the circuit. Now, what do we know about when resistors are connected in parallel? What do we know about the potential difference across their ends? Right? What do we know about that?
The potential difference is the same, sir. From one end
Right.
and it's the same in both ends. Because if one is high on one end, on the other end which is low, which is all going to be the same, sir.
Right. So in parallel, Alia,
Yes, sir.
right, you following?
Yes, sir.
when resistors are connected in parallel, the potential difference across their ends is the same, right? So when resistors are connected in parallel, the potential difference across their ends is the same. Anisha,
Yes, sir.
you can appreciate that?
Yes, sir.
Okay, so now, in that case now, what would be the potential difference across R1? In other words, what's going to be the potential difference across here and here? What's going to be the potential difference?
Sorry, 6 amps.
Potential difference, should get something like volts. What would it be?
Sorry, 12.
Why 12?
Sorry, because in parallel, the voltage is the same.
Right? And remember, R1 is connected across the 12-volt battery, right? So the potential difference across these points will be the same as the potential difference of the battery. Can we agree to that?
Yes, sir.
Yes.
Okay? So then now, to find the current through R1, which will be measured by A2, we can say I for the current is equal to what?
V over R.
Right? So I is equal to V over R. What's V? V
12.
will be the potential difference across R1, which is
12.
12 volts, and R would be what?
2.
2 is 2, they said?
Yes, sir.
Yes, 2 ohms, right? Good. 2 ohms. So this works out to be what?
6 amps.
6 amperes. Fair
In
enough?
this case, sir, we don't actually put the R2 and the R3, right?
No, we don't, because check the circuit again. A1 is connected in the branch with just R1 right here, based on how I label it. So we want to know the current. So this ammeter right here is actually measuring the current flowing through R1, which is the 2 ohm resistor right here. Cool?
Yes, sir.
All right. So now, and again, we use V, which is the potential difference across the R1 resistor. All right, so can I go again?
Yes, sir.
All right, so number 4. So let's go quickly now. So number 4 says we're to state Newton's 3 laws of motion. So let's go. Somebody tell me the first law.
Sir, the first law
There is
says
no.
that
First of all,
Wait.
uh, um,
Hold on. Wait. Come on. I mean, let's just be aware. I mean, if somebody is already speaking, let's just give them a chance, right? Because it's gonna create, confusion, with so many persons, right? And I don't want to say, all right, raise the hands, because I mean that I have to come back to the messages to see who is raising their hand, right? So, Kavan, I see you raise your hand politely, so let me let you go ahead.
Thank you, sir. Newton's first law states that a body in motion stays in motion while a body at rest stays at rest.
Right, a body in motion, right, will stay in motion, and what?
While a body at rest will stay at rest
Okay,
unless acted upon by an unbalanced force.
okay, good. Right, so we want to mention that, okay, that unbalance or that net force. But let me just add a little more to what you said right here. So a body in motion will stay in motion, right? All right, let's see. Let me add it to it, because based on what I want to add, so a body in motion will continue or will remain. All right, let's say will stay in motion, right? Because essentially, what I wanted to do really was I wanted to actually mention that, okay, it's going to remain in motion in a straight line, right, at constant velocity, because that is exactly what Newton's actually said. So let me just modify your answer a little bit. So a body in motion will continue in motion in a straight line, S-T-R-A-I-G-H-T, in a straight line at constant velocity, right? And a body in motion, what you said, Kelvin? Sorry, a body at rest. A body at rest will? Kelvin still here? No, it's stream not frozen. I'm waiting. Come on, you're not here.
Oh,
Let us
sorry,
finish
sir.
this. Let's go.
I did just go for some water.
Okay, okay.
Yes, a body
And
at
a
rest
body
will
at rest,
stay
what
at
happened
rest.
to it? Right? Stay at rest. At rest. Unless,
A
right,
force is
acted,
act upon it.
right? Not there's a force, right? Acted upon by a net force or an unbalanced force. Right? Net or an unbalanced force. Because if we have a rock, a stone right here, let's say this is a stone, right? A big boulder, right? And let us say we try to push that stone, right? We try to push that stone, right? Now, that stone, it may not move, or it's very unlikely to move because the force that we apply, right, is being balanced out, put it that way, by the resistive force of the boulder. So it's not going to move. That is why we say that, okay, it must be acted upon by an unbalanced force. So we need to actually produce a force that is larger or greater than that resistive force to set that stone in motion if it is at rest. Cool?
So, sir.
Right? Who's taking up the second law? Who's taking the second law? No one?
Sir, the second law states that the rate of change of momentum is directly proportional to the force applied.
Right? So the rate of change of momentum of an object is directly proportional to the applied force, right? And we can leave it at that, or we can actually mention the fact that, okay, the rate of change of momentum, it will occur or it will act in the direction of the applied force. So directly proportional to the applied force. Okay?
So, it could apply to the magnitude and direction.
Magnitude, repeat, please.
The rate of change in momentum is equal to the magnitude and direction.
Of the applied force, yes. So third law.
For for every action in force in nature, there is an equal opposite reaction.
Okay, so for every action there's an opposite but equal reaction, right? And a more robust definition for the third law
When a
is
body, a body A act upon body A act a force on body B, the huh? Something like that.
Um,
so more clearly, the third law says that if body A, and we should be able to, visualize these concepts, So if body A exerts a force on body B, body, B-O-D-Y, body B will in turn will exert an equal but opposite force on body A. So if we consider we have a brick wall right here, right, and somebody tries to push that brick wall with a force, what we're going to see is that the brick wall will actually push back, right, with an equal but opposite force, right? And similarly, when you sit on a chair, the reason why the chair does not fall is because when you apply your weight onto the chair, which is a force, hopefully the chair is able to exert an equal but opposite force on you. Otherwise, if the chair is not able to provide an equal and opposite force on you, what will happen?
Sorry, it would break.
Chair would break, right? And you're gonna fall straight to the ground, right? So you're gonna accelerate downward. So you're gonna experience a change in momentum, right? You're gonna experience a change in momentum in that case. All right. So anybody have any question on the Newton's laws right here?
I don't believe so, sir.
Yeah, but let's hear from the participants. You know, what do you have questions?
Yeah, yes, sir.
No. All right. So let's continue then. All right. So next one now says that in a crash test, a car traveling at a constant velocity of 26 meters per second crashes into a wall and is brought to rest. Calculate the initial momentum of a 70 kilogram test dummy in the car before the crash. So now, what would this thing?
Sir, momentum.
That's the moment.
Mass times the velocity.
Velocity.
Right, so the momentum, right, momentum P is equal to, hold on a second. So the momentum P is equal to the mass multiplied by the velocity. So the mass of the dummy was 70 kilograms, and the dummy was moving with a velocity of what?
Sorry, 26 miles per hour.
26 meters per second.
Okay, so 26 meters per second, and this works out to be
1,820 kilometers per second. Kilograms meters per second.
right? Okay, 1,820 kilograms meters per second. All right. Next thing says we have to calculate average force exerted on the dummy by the seatbelt during the crash. If the duration of the collision is 0.1 second. So how do we work this one?
Sorry, use the impulse formula.
Impulse formula. Tell me about that.
Sorry, to the change in momentum equal the force times the change in time. That one.
Okay, so the change in momentum. So mv minus mu is equal to F delta T. That's what you said?
Oh, sorry, wrong with
No. You're not wrong, You're good, man. You're good. Trust me, you're good. But however, let's kind of, without thinking about, okay.
She's on it, you know.
Hold on.
She's on it. You just use force equal to mv minus mu divided by time.
Right, but as I said, I wanted to just point out, the equation, and I mean, it's good, but because I already mentioned impulse, right? I'm not sure how many persons here know about impulse. But here know about impulse? Yes, no?
Impulse is 1 equal ft.
Yes, impulse is equal to the force. Well, force times time. Yes, that's impulse. All right, but let's just double back for a minute and consider Newton's second law. So
You can't use M is equal to, in brackets, B minus U over T.
Hold on a second. Let me just outline this first. All right, what's going on? So let's consider Newton's second law, this one right here, for a second. So it says that the rate of change of momentum is directly proportional to the applied force. So from this, we can write an expression where we say that, okay, the applied force F is equal to the rate of, well, it is directly proportional to the rate of change of momentum. So really and truly, what we would get is F is directly proportional to the change in momentum over time. All right? Now, the change in momentum is just simply mv minus mu. So what we can do is we can replace the directly proportional sign on a constant. Let us say that constant is equal to 1. So what we would get is we're going to get F is equal to 1 times the change in momentum, which is mv minus mu divided by t. Now, we can further simplify this, so we can say F is equal to, since we have m being common, we can say m into v minus u divided by the time t. Are you comfortable with this?
Yes, sir.
So now, let's say we need to find the average force. So F right here would represent the average force. So now, what we can do now is we can say, okay, the mass of the was, yes?
You can say force can either be velocity, it's velocity too. I said
I mean
velocity.
force being velocity, explain. As in force is equal to velocity?
I was thinking of the other equation.
No. No, 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 not that, no, no, no. Right? So the mass of the dummy was what? 80 kilogram? What was it? Or 70 kilogram? Right? The final velocity would be what?
0.
0. Right? Why 0?
So because it was brought to rest.
Right? So it would have been brought to rest. So 0 meters per second minus u, which was
26 meters per second.
right, 26 meters per second. So meters per second. I will divide that by the time, which is 0.1 seconds. So 0.1 second. So in simplification, now we're going to have 70 minus negative, sorry, 70 times negative 26 would give us what?
So negative 1,820.
Like that?
Sorry, 20. 20.
Oh, all right, tell me the digits again.
So 1820.
20, okay. I will divide this now by 0.1 seconds, and this works out to be what?
So negative 18,200 newtons.
Newtons. So why we have the negative sign right here? Anybody know?
Negative times positive will be negative.
So because of direction.
No. Right, because of the direction that the force is applied. So remember, the seatbelt, right, will be trying to restrain the dummy. So the seatbelt will be acting against the dummy. So it will be acting in the opposite direction to the movement of the dummy. So as we're working these questions, we want to be thinking about, okay, the fact that force is a vector quantity, right? Momentum also is a vector quantity. What else in this scenario would be a vector quantity?
Velocity.
Velocity, right? So those are vector quantities, so they will have magnitude as well as a direction. So the negative right here just indicates that, okay, it's acting against the dummy. Cool?
Yes, sir.
Right? Now, for this one, it says, with the removal of all protective features, the dummy was subjected to another crash test with the same initial speed. This time, it was subjected to a lethal decelerating force of 45,000 newtons. I want to calculate the duration of this collision. So, using Newton's second law, again, F is equal to m into v minus u over t. In this case, we're trying to find t, so we can cross multiply, right? We're going to get ft is equal to m into v minus u, right? We're trying to find t we're trying to find. So we're going to divide this one by f, divide here by f. So then, we're going to see that t is going to be equal to m into v minus u over the force. So now, T now is going to be mass, again, is 70 kilogram. V is 0 meters per second minus 26 meters per second. And we divide that now by the force, which is this value, 45,000 newtons. So T now is going to be, this, we calculated this from before, it was all like minus 1,820.
Yes.
That's how it was. And we divide it by this now, 4500 newtons. This would be?
Negative 0.04.
Okay, oh, by the way, you know, I kind of went tired of myself. All right. So they said a decelerating force. So really and truly, it's going to be negative because we don't expect the time to be negative or positive because time is not a vector quantity. So the decelerating force will be acting in opposition to the dummy. So it's going to be negative. So these two negatives will just cancel out each other. So what would be the time?
0.04
Again? Seconds. Cool? All right, next question. So let's go right here now. So it says that Newton and Huygens were two of the scientists who made significant contributions to the modern view of light as embracing both a wave and a particle nature. State what evidence each proposed and whether this evidence supported the wave theory or the particle theory. So first of all, let us state which theory each scientist was proposing. So Newton was known for what theory of light?
Visible light.
And we're talking about the theory. What theory of light did Newton put forward?
A particle.
White.
Repeat?
That a particle with.
Right. So Newton was known for his particle theory of light. Right? So Newton was known for his particle theory. And then Huygens now was known
Wave theory.
for his what? Right? So wave theory. Right? Now what evidence did Newton bring forward?
So that light particle is made up of.
Well, that would be the conclusion, but
I think that he
yes?
said that light could travel to water very quickly. I think that was it.
No,
I don't know.
No, that's not it.
The diffraction of light.
Diffraction of light. Sure, that was in relation to the particle theory.
No, that wasn't.
That would more sound like for the wave theory. So, with the particle theory, what Newton would have brought forward, he would have suggested that, or he would have actually shown that light can be reflected. Right? Light can be reflected. Just like, if you have a tennis ball, and tennis ball, we know, we can consider that to be a particle. Right? So if we throw a tennis ball to a wall, and it hits the wall, it's going to reflect. Right? Because what Newton was saying is that light is made up of tiny particles. Well, it is made up of particles that he called corpuscles. So light is made up of particles called corpuscles, right? So you would have said that, okay, light can be reflected. So that would be, his way of saying that, okay, light must be a particle, right? What else?
And he said something about light can travel fast, in a medium of light, medium of water or so.
No, not quite. Anybody, anyone have any ideas?
So light is made up of color that appears white. Is that one? No.
Not quite. Well, ultimately, he would have shown that light is made up of
Light
different
is formula length.
colors. Huh?
Light passes through a lens.
Sir, are you talking about visible light?
No more. Yeah, we're talking about visible light. We're talking about visible light. So you would have said that, okay, light can undergo reflection,
Yeah.
right? Anything else? Anything else? So another evidence brought forward by Newton was that light can be refracted, right? So light can be refracted. So these were two evidence, right, that Newton would have brought forward to say, okay, light must be a particle. So if you can just consider that stream of particles moving between two mediums, when they enter a medium, let us say of a different density, optical density that is, they're going to experience a change in direction, right? And that change in direction is what we constitute as refraction. Okay?
Great, sir.
So these were two evidence that were brought forward by Newton relating to the fact that light is a particle. Okay? Now for arguments now, let's talk about the two evidence. So the first one was that light can be diffracted, right? Or light can undergo diffraction. Right? So light can be diffracted, right? Anything else?
Light can move slow through water, sir.
No, man, no, man, no, man, no, 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 no.
Light
No, no,
travel in
no.
a
That wouldn't
straight
be.
line.
Next one. No, not really.
No, light
So,
can move fast.
hold on a second, hold on a second, hold on a second. Hold on a second, let's kind of take it slowly. So, we said that light can be diffracted. Now, there was another scientist who, go ahead, Sarah.
Sir, bend. It can bend.
Right, that would be the refraction. The quote bending. That would be the refraction. Now, there was another scientist who did some experiment, right, that, pioneered Huygens' principle or Huygens' theory of light. And that scientist was by the name of right? What did Young do? Anybody know about Young's experiment?
Not quite, if I can remember.
So Young did an experiment to
Oh,
show
um,
somebody saying something.
yes, he did an experiment where he had a box and he put two, two holes on the top, basically a spectrum. He created a spectrum where light can be pierced through a hole and it is diffracted, basically.
Well, what he did was a famous double slit experiment. And from that double slit experiment, it showed that light waves or light can interfere, right? Light waves interfere, so therefore, light interferes, so therefore they would have said that, okay, that must mean that it must be a wave. So light can interfere, right? And we're able to see that series of, what is it called again? Bright and dark fringes due to the constructive and destructive interference of light. Okay?
Yes, sir.
Right? Anybody have any question?
Sir, is there any more scientists that we have to know in case we follow this?
Yes, you have to know about
From
Rutherford
Planck.
and Chadwick and Planck. No, you don't have to know about
You
Planck
mean J.J. Johnson?
at CSEC. Yeah, you need to know J.J. Thompson and those scientists. Right? So let's move to this one now. So a homemade projector is constructed from a cardboard box, a cell phone stand to hold the phone upright, and a magnifying glass embedded into one face of the box as shown in figure 5. The focal length of the lens is 15 centimeters. So now, it says here that we're to suggest a reason, an appropriate distance from the lens at which the phone should be placed in order to get a magnified image on an external screen. So what would we say for this one?
Can you repeat that, please?
Yes, the question says we're to suggest with a reason an appropriate distance from the lens at which the phone should be placed in order to get a magnified image on an external screen.
It should be,
All right, so let's kind of just, see how we can break down this question. So they said that we want to form an image on an external screen. So the image that we want to produce, can we determine if it's going to be real or virtual? Why
because
virtual?
there's only image on viewed on a projector is visual.
Well, look at the statement right here. It says on an external screen. Now, once we have an image on a screen, it will always be real. A real image is the only image that we can actually view on a screen. Okay? So a real image can be projected or can be shown on a screen.
Sir, so
Okay?
then, since you know that's going to form a real image, sir, the distance have to be greater than the focal length.
Absolutely. Right? So the distance will have to be greater than the focal length. Now, the next thing now, it says we want a magnified image. A magnified image. So now we have to be a little more precise in terms of, okay, where we're going to place that object to get a real image, yes. So we say that it must be greater than the focal length, right? So where exactly would we place our object to get a magnified image, magnified real image?
Turn the
About
upper
half the focal length. About half
Huh?
of it.
No, but we just said that it has to
Sir,
be
the
greater
Oh,
than the
upper
focal
side,
length.
the next. Turn the next
Huh?
side. Well,
All right. All right, let's kind of sketch it out so we can see some visual thing. So let's say that's the lens right there. Let's just say this is our principal focus. That's our principal focus. So our focal length would be this distance here, right? So we're saying now, number one, the object must be placed at a distance greater than the focal length, right?
correct.
But how far from the lens we're going to put it? What suggestion would we say in terms of a
Would it
distance from
be
the lens?
two times the focal length?
2 times the focal length? You say 2
Yes,
times the
that I
focal
said.
length?
Is it?
Alright, hold on a second. So let us say if this is 2f right here, so this is f1, this is 2f1, right? So you're saying that you're going to place the object at this distance, right?
Yes, sir.
Todd?
Yes, sir.
So anybody knows what would happen to the image in terms of its size if we place it at a distance that is equal to 2 times the focal length?
So the object is going to be the same size as the.
Right, exactly. The image will be the same size as the object. If it is placed at a distance equal to 2 times the focal length, the image height or the image size is going to be equal to the object size. Okay? Yes?
Correct.
What would happen if we place it, let us say, between f and 2f1? F1 and 2f1, what would be the image size?
So it's
Anybody
going to
know?
be magnified.
Magnifying.
It's going to be magnified. It's going to be magnified, right? So placing the object at a distance greater, or in other words, at a distance equal to f, which is the focal length, and 2f, which is 2 times the focal length, will allow us to get a magnified image, a magnified real image. With me so far?
We could just go
What do
it
you
over.
think? Right. So I'm saying, in order for us to get a real image using a convex lens, right? A real magnified image, we have to be specific. A magnified real image, our object distance must be between f1, which is our principal focus, and 2f, which is 2 times the principal focus. Now that equates to a distance between the focal length f and we could say 2f, right? So the object must be between f and 2f, okay? Just as what we have right here with our red arrow. See this?
So sorry, put the image,
Yes,
the
no?
object between F1 and F2.
Yes. F1 and 2f1. 2f1. F1 again is the principal focus. 2f1 is 2 times the principal
Oh,
focus.
right. And when you do this, it's going to make it becomes
Right?
way more larger than the actual object.
Right. You're going to get it magnified. Right? So they say we need to choose an appropriate distance. So what would we say? And again, consider that the focal length is this value. What would we tell them? What are we going to tell them? Anybody know?
They will place it greater than the vocal length.
Okay? But like what? Like 100? Because 100 is greater than the focal length, you know. What's the focal length again?
Like you could place it like 20 centimeters.
Okay? So 20 centimeters would be greater than the focal length, but it is less than 2 times the focal length. So in other words, the object must be between 15 centimeters. So you're not going to put that 15 centimeters. So it must be greater than 15 centimeters, but it must be less than 30 centimeters. Right? So it must be greater than 15 but less than 30 centimeters. Okay? So what distance?
So how about 25?
25. Okay. Object can be placed at a distance of, we say, 25 centimeters from the lens. Everybody okay with this?
But one more thing I wanted to find out, right? Not only virtual image could be
Repeat for me.
one thing I wanted to find out, right? It's not only the virtual images with a projector, I could have a real image too.
No. Hold on a second. Hold on a second. Once you're using a convex lens as a projector, as what this scenario is talking about, the image is always real. The only time we will use or we will actually get a virtual image from a convex lens is when we're using the convex lens as a magnifying glass.
Okay.
Got that?
Yeah, but where the lens in this question? What I see is the box.
This is the lens.
Oh, okay.
That's the lens. Right? Because remember, inside a magnifying glass is a convex lens. Right? This is our convex lens right here.
Oh.
Okay? So don't get sidetracked by the term magnifying glass, right? And think about a virtual image, right? Even though we have a magnifying glass right here, you have to think of it in terms of a convex lens, because a magnifying glass is in fact a convex lens.
Okay. All right.
Okay?
I understand now.
Anybody else have any question? Anybody else have any question? Alia?
No, sir.
And everything
Yes,
is clear
sir.
for you? Okay. Karagina? Not hearing from you, Karagina. Kara? Do you have questions? Okay. I just want to make sure everyone is clear on this, all right? So we're going to place the object between 15 centimeters and 30 centimeters. Again, not inclusive 15 nor 30. All right, is there a question somewhere? Okay. All right, so that's that. So, and again, as we said now, the reason why we do that now is that to produce a real magnified image, the object must be between f, which is the focal length, and 2f, which is 2 times the focal length. Clear? Come on in. Mitchell, that's clear for you?
Yes, sir.
All right, so that's that. So let's continue.
Hold on, sir. Let me
Now
get
it
a
says that if,
screenshot, please.
right, screen it, shut it. Johnny, can you hear me loud and clear?
Yes, sir.
Okay, any questions so far?
No, sir.
Okay. All right, so let's go right here now. So the next question here says that if the phone is placed 20 centimeters from the lens, calculate the distance the screen must be placed from the lens in order to obtain a clear image of the phone. So how we go about this question?
Using the
Lens formula.
Lens
1
formula, which
over F
is
is equals to 1 over U. That's 1 over.
plus 1 over V. So now, in this case, what do we know? What do we know in this question? What do we know? What information do we know?
we have the object distance
Okay, so we have U, which is
20 centimeters, the focal length of 15 centimeters.
okay, and we're trying to find
Yes, sir.
V, right? So V is unknown. So now let's first rearrange to make V the subject. So when we do that, we're going to get 1 upon V is equal to 1 upon F minus 1 upon U. So now, substituting, F is 15, so we have 15 minus 1 upon U, which is 20. So our LCM for this case would be LCM?
60.
Okay, 60. So 15 into 60 goes what? 4 times. So we have 4 times 1 is 4. Minus 20 into 60 goes 3 times. So we have 3 times 1 is 3. So now we're going to see that 1 upon V is equal to 4 minus 3, which is 1 over 60. So again, we can reciprocate both fractions. So reciprocate 1 upon V, we're going to get V over 1, or simply V, and that will be equal to 60 over 1, or simply 60 centimeters. Okay?
Yes, sir.
Right, so everyone okay with this?
Yes, sir.
Okay. All right, so let's continue. So here's the next question now. This question here says that we're to describe how the graph of volume versus temperature in Celsius of a gas can be used to derive the Kelvin scale. So anybody
We extend the axis.
extend which axis?
The X, the X.
Okay? But how would that help us? Just extending the axis. I'm not sure what you mean. What do you mean by just extending the axis? What do you mean?
Like to show like if it's like so like
Sir,
Yes, help us out.
sir, for Celsius, you know that in temperature is absolute zero. So it will be on the zero scale. For Kelvin, we all know Kelvin is 273. So it will be negative 0.73 degrees for the Celsius scale.
Yes, but
Unlike
right, but what you're gonna tell examiner? What you're gonna tell examiner? No, listen. No. We have to just be um, appreciative of the question that the examiner is asking. The examiner is asking how the graph of volume versus temperature in Celsius of a gas can be used to derive the Kelvin scale. So we want to tell the examiner clearly how a graph of volume versus temperature in Celsius can be used to derive the Kelvin scale. So how we're gonna go about this one? Would we want to show the examiner a graph of volume against temperature?
Yes, sir.
Yes, yes.
Yes, might want to do that. So we could start by saying, okay, we draw or we sketch the graph, right, of volume against temperature. Because here we're talking about extending axis and all that, which might become helpful down the line. But again, we want to be clear in the way, we communicate ourselves to the examiner. So we could draw the axes or sketch the graph, sorry, of volume, let's say volume in cubic meters, against temperature in what degree, what they
Kelvin.
said?
In Celsius.
In Celsius. In Celsius, right? So degrees Celsius. So now, if we plot a graph of volume against temperature in Celsius, what type of graph would we expect to get?
Straight line.
Straight line, showing what type of relationship?
Inverse.
So a proportional relationship.
Directly proportional.
Proportional, right? Proportional. Volume is directly proportional to temperature in Kelvin, right? When pressure is constant based on Charles' law, but again, temperature must be in Kelvin. So because we have temperature in Celsius, we're going to get not a directly proportional relationship, but instead a proportional relationship. So how do we show a proportional relationship?
So it mustn't pass through
Huh?
the origin. So it's no, we're gonna make a line that like hits the y-axis, but don't hit the origin.
Right? Right. So we're gonna get something like
Right.
this. Right? So this is the graph we're gonna get. So let me just use one stroke, one line. So we're gonna get a graph like this. Right? Because the volume is proportional to the temperature in Celsius. Now, what we can do now from here is we can now extrapolate the graph, right, towards the negative x-axis. So let me just extend the axis now as what we're saying. So extend the x-axis. Let's say we'll put the origin right here, 0. Then what we do is we can extend our graph using a broken line like that to the negative x-axis. And what we're going to see now is that we're going to be able to read off a value right here, which corresponds to the temperature of the gas when its volume is 0. And this value will be minus 273 degrees Celsius, which actually corresponds to 0 Kelvin. So now, what we can say now is we can say, okay, a graph of volume against temperature in degrees Celsius can be plotted, right? Can be plotted. Right, then if we extrapolate the graph to find temperature at 0 cm cube, the value would correspond to minus 273 degrees Celsius, which is 0 on the Kelvin scale. Okay? Yes, no?
Yes, sir, but wait, don't change it as it.
Okay. So again, as we're going through the questions, remember, we're having a conversation with the examiner, right? And we want to be and remember, you're not in front of the examiner to, re-explain yourself or what can I say, expound on what you're saying. So you want to just be as clear as possible when you're responding to the question, right? And that also ties back to our ability to first understand and appreciate the question when giving our responses. Yes, Todd, go ahead.
Sir, could we draw the diagram where you just showing here on the paper? Could we do that and then
But you wouldn't get
explain?
full marks. Yeah, exactly as we did right here.
So it's what if we just explain and then draw the diagram?
Again, in that case, no, you'd have to be as descriptive as you can, right? But as I said, usually when they say explain, I always recommend, using a diagram to support your explanation wherever possible. Okay?
Oh, thank you for that point.
Yeah, man. Ready again, Sarah?
Yes, sir.
Yes, Johnny, you have questions?
No, sir.
When you say extrapolate
Okay.
the graph, what takes it?
So, somebody said something?
Sure, what does the term extrapolate mean? Like when you extrapolate?
Extrapolate, okay. Extrapolate just simply means, in this case, it just simply means that we're going to extend the graph until it touches, extend the line until it touches the, what do you call this again? The x-axis. Until it touches the x-axis. Now, extrapolation just simply means that, okay, we're trying to find out a value, right, on either axis, given a certain value. So in this case, what we're doing is we're extrapolating so we can find the temperature when the volume is 0 cm cube. But based on our graph right here, we have to extend the graph. So we extend it like this so we can find the temperature when the volume is 0 cm cube. 0 cm cube. Right, and in this case, it's going to correspond to our x-intercept. All right, so that's that. Then now it says now state the mathematical relationship between the Kelvin and the Celsius temperature scales.
Sir,
So what do
K
we say?
equals the plus 200.
Repeat.
Sir, Kelvin equals the degree Celsius plus 230.
Okay. So so the temperature in Kelvin, right? So we could say T in Kelvin is equal to, let us say, theta in degrees Celsius plus 273. So what we simply do is we just simply add 273 in order to convert from Kelvin to Celsius. All right?
Yes, sir.
All right, okay. All right, yes. Right, so that's our mathematical relationship. So the temperature in Kelvin is our temperature in Celsius plus 273. So now, next question now says that when a piston traps a mass of gas in a cylinder. At 25 degrees Celsius, the pressure of the gas is 5 atmospheres when its volume is 50 milliliters. Calculate the volume of the gas if the pressure drops to 1 atmosphere at constant temperature. So once we say something about constant temperature, what's the first thing
Yes,
come
sir.
to mind?
Yeah, and you could
General
then
gas law.
Sir Boyle's law.
All right, okay, okay. All right, remember, I mean, we're trying to have a discussion at the same time, So, let's just be mindful of that in terms of, So, I hear somebody said general gas law, I hear Boyle's law. But let's say collectively, we know that this question has to do with something related to gas laws, right?
yes, sir.
Yes, yes.
Right? But yes, and they say that temperature is constant. So if the temperature is constant, which gas law specifically we got to
Boyle's
deal with?
law.
Well,
Right? Boyle's law, right? So remember, once temperature is constant, that's Boyle's law. Now, since we're given that the gas was at some initial temperature, temperature is constant, so the temperature will not change, right? So the initial temperature and the final temperature will be the same. But we're told that the pressure was 5 atmosphere initially, and its volume was 50 milliliters. And then the volume dropped to 1 atmosphere. So in that case now, we can write that our initial pressure, P1, times our initial volume, V1, must be equal to what?
P
P2,
times
V2.
P, P2 times V2. Now in this case, now they say we need to find the volume of the gas, right? When its pressure drops. So therefore we want to find V2. So let's make V2 the subject first thing, and then we'll take it from there. So we divide this one by P2, divide this one by P2. After doing that, we see that V2 is equal to P1 V1 over P2. So now, let me see what space we have. All right, so we can just substitute down here. So let's note down the values first of all. I like to do this with these kind of questions. So P1, what's P1?
Sir 5
5
atmospheres.
what? Right, 5 atmospheres. Now remember, 1 atmosphere is equal to what? Approximately what? Usually will give you in the question, but let's see. Anybody know? 1 atmosphere is equal to what?
1 Pascal, sir.
No, not 1 Pascal. More than that. 100 kilopascals. Right? 1 atmosphere is approximately 100 kilopascals. So P1 is 5 atmosphere. P2 is 1 atmosphere. Right? What else to say now? Thing there. T1. T1 is what? Oh, wait, do we need T? No, we don't need T1, right? Because the temperature is constant and we're dealing with Boyle's law. So we need V1.
50
What's V1?
milliliters.
Right? 50 ml. And, I'm sorry, V2 is
Unknown.
unknown, right? So that's what we're trying to find right here. So then, we're going to now put in the values. So we have 5 atmospheres. So we say 5 atmospheres multiplied by V1, which is 50 milliliters, divided by, and again, we could have used 5 times 10 to the, 500 kilopascals, because we just multiply 100 kilopascals by 5. But because the units are the same, they will cancel out. So we have 5 atmosphere times 50 milliliters divided by P2, which is 1 atmosphere. So therefore, now, this one works out to be what?
650 ml.
right? So V2 will be 250 milliliters. That's good?
You look great, sir.
All right? So, can we continue?
Yes, sir.
All right? So next one now says that after resetting the piston, the gas returns to its initial pressure and volume. If the volume is now fixed, so in this case, they're saying that the volume is now fixed while the gas is heated to 60 degrees Celsius. Calculate the final pressure of the gas. Somebody saying something?
The volume is constant, no?
Right, so the volume is constant. So if the volume is constant, which gas law we're going to
So
be
pressure
thinking
law.
about? Pressure law, right? And what does the pressure law say?
So the pressure law states that for a fixed mass of gas at constant, the pressure is directly proportional to the Kelvin temperature.
Right, repeat again.
So the pressure law states that for a fixed mass of gas at constant volume, the pressure is directly proportional to the Kelvin temperature or absolute temperature.
Right, absolutely. Very good. So now, in this case now, what we're told now is we're told that the piston was reset, and the volume is now fixed, right? And the gas was heated to 60 degrees Celsius, and we're to find the final pressure. So let's see what we know in this scenario. So we know, well, first of all, let's write our equation, because our equation is going to guide us in terms of what variables specifically we're going to be dealing with. So with the pressure law, we can write P1 over T1 is equal to P2 over T2. So in this case, P1, what's P1?
Sir, 5 atmosphere.
Right, 5 atmosphere. Why 5 atmosphere?
Because that was the initial pressure.
Right, and I said that it was reset, right? So the thing was reset, and right, when the temperature is 25 degrees Celsius, it has a pressure of 5 atmosphere. So P1 would be 5 atmosphere, and P2 would be what?
So it's unknown.
Unknown. T1 in this case would be?
Sir, 25 plus 273, which gives you 298.
Which is 298 Kelvin, and T2?
So it would be 60 plus 273, which gives 333.
330 how much?
33.
33 Kelvin, all right? So we have all the variables that we need to help us out, so we can now perform our calculation. So what we're trying to find, P2, so let's make P2 the subject. So we cross multiply like that. We're gonna get P1 T2 is equal to P2 T1. We're trying to find P2 divided by T1 divided by T1. Everyone following?
Yeah.
Regina,
Yes, sir.
right? So this one goes with this one. So we're going to have P2 is equal to P1 times T2 over T1. Ferguson? Ferguson still there? Ferguson? All is well? Okay, all right. So now, from here, it's just a matter of substituting our values. So let's put it right here. So we're going to have P2 is equal to P1, which is 5 atmospheres, multiplied by T2, which is this value. So 333 Kelvin, divided by T1, which is this one, 298 Kelvin. And this works out to be that P2 is what? What's the unit? I mean, what's the value, I should say?
Sir, 5.59 atmospheres.
atmospheres. Okay? Everybody
Yes,
agree?
sir.
Alright, so 5.59 atmospheres would be our pressure. Now, what would this value be in pascals? All right, let's say in kilopascals. What would this value be in kilopascals? Again, 1 atmosphere is 100 kilopascals. So what would this be in kilopascals?
559 kilopascals.
Right, so P2 would be 559 kilopascals, right? Or approximately 560
Sure, the
kilopascals.
value of the kilopascal was 100, or right? Or was it 1,000?
Repeat, please.
Was it 1,000 kilopascal or 100 kilopascal?
100
Okay, sorry.
kilopascals, right? 1 atmosphere is approximately 100 kilopascals. All right, so we're good with that?
Yes.
All right, I think we're on the last question now. So now, it says here that using fully labeled diagrams, define the principal focus of a convergent lens. What are we going to say for this? Or by the way, let's say we must use fully labeled diagrams. So we first would have to draw a diagram for a convergent lens, right? Yes?
Yes.
Now, what do we know about a convergent lens?
Cannot end.
Like,
So it's wider in the middle.
Right? It's wider in the middle or thicker in the middle. So our convergent lens would look something like this, like that, right? Roughly like that, you know? That would be our convergent lens, right? And so we need to define the principal focus. So now we're going to, by the way, we know that the principal focus will always be on the principal what?
axis.
Axis, right? So we're gonna put in our principal axis, let us say like that, right? And let's say we just indicate that, okay, this point is the center of the lens, right? And let's say we label it O for the optical center. Now, somewhere on the principal axis, we're going to have a focus that we call the principal focus, and let us say we put it on both sides. And here, let us say we call it F1 on this side, and this one we're going to say, okay, this is F2. So now that's how we need to define the principal focus of a convergent lens. So when talking about the principal focus of a convergent lens, we have to consider, let us say we had some rays of light. Can I use gray? No. Let's say we had some rays of light, some red rays. We had some rays of light like this, let us say, this one. All right, we had some rays of light, this one. What's going on? Hold on a second. You guys see my screen? Okay, all right. What's going on? Are you guys able to see my screen?
Yes, sir.
Yes.
So let us say we had 2 rays of light. Let us say these are parallel to the principal axis like that. Right? Now these rays, upon passing through the lens, because we have a convergent lens, what will happen to them?
So they're going to meet.
You're going to meet, right? Or converge. So they were going to refract and go like this through there. And this one goes like that. Right? Now, in terms of defining the principal focus, I mean, I'm doing this just to give everybody an appreciation for the action of a convergent lens, right? Now, what we see now is that these 2 rays of light, they actually converge, right? At a point. Now, the point at which they converge is called our principal focus. So, in defining the principal focus, we can say that this is, let me just put it, the point on the principal axis where rays of light initially parallel to where?
To the principal axis.
Right, to the principal axis, they converge after passing through the lens, right? That would be our definition for the principal axis of a converging lens, okay? Cool?
Yeah.
Right? Now, for the diverging lens now, we know
Yeah.
that the converging was
Your
thicker in the
turn,
middle.
please. I need
So the diverging, what would happen to the diverging in terms of its shape?
So it's going to be thicker at the ends.
Right? Thicker at the ends, right? So we're going to have, let's say, if I can sketch it out like that, that. So this is our concave or divergent lens. So now we're going to have our, what's going on? We're going to have our principal axis like that. Right? And again, just like before, I'm going to define my 2 points, which are the principal focus, and I'm going to define my optical center here, right? And let's say this is F1, F2. So now again, considering parallel rays of light, let's say one like that, one like this, right? Once they pass through the lens, they will meet at the principal focus, correct?
correct.
Sure?
No,
The
sir, they
divergent
could
lens?
move.
Oh, they will divert, sir. They will divert edge of the
Right. Right. So we want to pay attention, right? So they're going to diverge like that. Right? And this one is going to diverge like that. Now, because these two rays they diverge like this, we know that light travels in a straight line. So, upon viewing, let us say, upon using this lens, what we're going to see is that, or as a matter of fact, what our eyes will actually perceive is our eyes are going to perceive that these rays were coming from a common point, right? So what we can do is if we were to trace these rays behind the lens, sorry, in front of the lens, in other words, trace them towards this direction, what we're going to see is that upon tracing these, the two rays will appear to be coming from this point right here. And this point, as indicated right here, would be our principal focus. So when defining the principal focus for a concave or a divergent lens, we will say that it's the point, so the point on the principal axis, let me just write out the word, don't be lazy, on the principal axis where rays of light initially parallel to the principal axis, they appear to come from after passing through the lens. Okay, but you got that? We got that. Okay. Vashti?
I'm trying to figure out, after you say appear to something, I'm trying to figure out that word.
Oh, appear to come from.
Okay.
Right? Appear to come
Sir,
from.
can I go back to the first one, please? Yes,
First
sir.
diagram. I just want to fix this time because it just look kind of weird to me. Now that I look back at it. I mean, it's the same thing, but I just, you know, kind of bring it a little closer. It just look weird, you know, all the way up that side. Right, like that. Look a little better. Right, in a sense, I guess.
Yes, sir.
And then this one here. All right, so we're okay?
Yes, sir.
All right, so next one now says that an object of height 7.2 centimeters is placed 18 centimeters from a converging lens of focal length 12 centimeters, and we're to determine the image distance. So again, we're going to call upon the use of our lens equation, which is 1 upon f is equal to 1 upon v plus 1 upon u. Yes?
Yes, sir.
So now let's take down some information. So f is 12 centimeters. V is unknown. And U is what? What's U?
7.2 centimeters.
7.2?
Sorry.
So,
Sir,
by the
18?
object.
18, right? So it was placed 18 centimeters from the lens. So the distance from the lens, well, the object distance from the lens, kind of, you know, the object distance from the lens is the object distance. In other words, how far the object is placed from the lens is the object distance. So the object is placed 18 centimeters, but its height is 7.2. So we just want to be clear and aware of these things. So U is 18 centimeters. So now, just a matter of calculation here. So we're trying to find V. So again, we say 1 upon V is 1 upon F minus 1 upon U. So this now becomes 1 upon F, which is 12, minus 1 upon U, which is 18, 1 upon 18. So we have 1 upon V. Come on, hold on. So we have 1 upon V is equal to 1 upon 12 minus 1 upon 18. LCM for this would be?
36.
Alright, so 36. So 12 into 36?
3.
3 times. So we have 3 times 1, which is 3. Minus this into that goes 2 times. So we're going to have 2 right there. So 1 upon V is 1 over 36. So therefore, we can say that when we reciprocate both, we're going to get that V is equal to
36 centimeters.
right, 36 centimeters. All right, that's good. Yes, no?
Yes, sir.
All right. So next thing that we need to do is to determine the magnification. Or we'll find magnification.
Sir, magnification
Equal to?
Sir, it would equal the image distance over the object distance.
Right, image distance over the object distance. So in this case now, we're going to have V, which is 36, divided by the object distance. What was it?
7.2.
18.
Object distance, 18, right? 18, distance, 18 centimeters. So then now this works out to be?
Yes, sir.
2, right? 2
No, sir,
centimeters.
just 2. There's no units.
Just 2, right? Just 2. There's no unit because these cancel, right? So 2 is our magnification. Now it says now we're to find the height of the image. So we're going to find the height of the image. Let me, Todd, go ahead.
Sir, sorry, my screen shut off. Can you just return where we're at the divergence and this I can take some screenshots, please?
All right.
Go down.
Got that? Have it?
Yes, sir.
All right. We just did these calculations a while ago.
All right, carry turn.
All right. So now, we want to find the height of the image. So how we do this now?
You can use the magnification equals the image height over the object height, and then you transpose for the image height.
Over the object height. So therefore, hi, always be like that, whatever that is, height. So therefore now, what we trying to find? Image height. So the image height then now, right, after transposing will simply be equal to the magnification m multiplied by the object height. Right, so let's say now that our image height, so the image height then it will be equal to the magnification, which is 2. Magnification was 2, right?
Yes, sir.
So
And our object height was
7.2,
centimeters. So this works out to be
14.4 centimeters.
14.4 centimeters. All right. And then finally, it says we're to state whether the image formed is real or virtual.
Sir, real.
Is the image real?
Yes, sir.
And why we say it's real?
Sir, because it got a positive value.
Okay, we got a positive value for what?
Sir, for the image distance.
For image distance, right? So we got a positive value for the image distance, yes? So that tells us that we're dealing with a real image. Now also, because of the fact that the object distance, where is it? 18 centimeters is greater than the focal length, that simply means that our image is going to be, or the object will produce a real image, or in other words, a real image will be produced. Once the object distance is greater than the focal length for a convex lens, we always get a real image. If the object distance is less than the focal length for a convex lens, we get a what type of image?
Virtual.
A virtual image. Right? A virtual image. So that's that. Any questions? So yeah, let me just put an answer here. So this is, we're going to say that the image is real. Now in terms of a real image is always on the opposite side of a lens, right? It is only produced by a convex lens or a converging lens. A real image can be formed on a screen, right? And a real image actually has light rays traveling from it into our eyes. That is why it is able to be seen on a screen.
Right? So it's not in a real image is not formed in a concave.
Concave? No, concave only produce virtual.
All right.
Only produce virtual image.
So you say it has light?
Yeah, light rays actually travel from a real image into our eyes.
Yes, sir.
Okay? So are there any questions? There's some we covered here.
No, sir.
Okay. Johnny, any question from
No,
you?
sir.
Okay. All right, so it's now 1:05. Also, we'll leave it at this till tomorrow.
Yeah, tomorrow again.
Yes. Sir, what time tomorrow?
2 o'clock. 2 o'clock tomorrow. So I'm going to set up the thing and send it out so you guys can be able to join using the link.
Okay, thank you, sir.
Yeah, man, cool. Oh, by the way, this solution document will be added to the link, so you'll be able to access it.
Good,
So
good.
which link?
So you're the best.
Um,
I saw which link.
hold on a second. Hold on a second. Hold on a second. I see a message in the chat. Brooke, I see you asking about how we got three. Three for what? What are we talking about? The last lens question? Where exactly are you talking about? Three? Three for what? The magnification. Oh, the magnification, did we get three or was it two? It's two we got. Two we got.
So which part is sending this?
Okay. Gonna send it in the email link.
Also, which part you give me the email? It will be there.
Yes.
Alright.
The distance part. Distance part. Distance part. Image distance part. Oh, we got 36 centimeters for the image distance.
So one more thing, but
We
in
got 36 for the image distance. Just hold on, Chinese, please. Let me just finalize. Okay, so you're clear now? Let me know if you're clear on what we're talking about. Where you got three? Where three? I don't see any three. What three are you talking about? Oh, you mean in the fraction? Yes, the document will be available. You mean right here? We said 12 into 36 goes three times. That's how we got the three here. So we divide this number denominator by our LCM, or we divide this number into our LCM, and we got three. So we divide 12 into 36 and got three. Make sense now? Okay, perfect. Yes, this document will be made available. I'm going to save it and actually upload it to the link, so you'll be able to access it from the link right away. All right?
yes,
Okay,
sir.
Shanice?
Yeah, I wanted to find out
Perfect.
in a convex